Am I audible? Audible to everyone? Okay. All right. Let's start then. I think we can start. So maybe you guys can also become आत्मनिर्भर. तो क्लासेस बंद कर देते हैं. आत्मनिर्भर भारत. बेस्ट है. मतलब एक अनाउंसमेंट हम लोग भी करते हैं मोदी जी के सेशन के बाद. All right. Let's start then. यार कुछ मिला नहीं, बिना मतलब आधा घंटा खराब कर दिया. Okay. So can anyone summarize what we did did yesterday in dynamic programming for the interest of everyone? Should I take up a person? Maybe Drishan, can you summarize what we did yesterday?
Sir.
Yeah.
So we saw the big picture dynamic programming, how we can combine subproblems to solve a bigger problem, how we can reuse the solutions to previously formed subproblems, so we don't have to redo them.
Yeah.
There are two general kinds of problems: optimization problems and combinatorial problems.
Yeah.
Then we looked at the Hausdorff problem.
Yeah.
So we saw the kind of decision we took in this case. So we looked at the smallest possible case, found the best solution to that, and then checked for the next, and checked the bigger and bigger cases.
Yeah.
So until we found the biggest possible case, which is the answer.
Yeah.
Then we did the circular case when the houses are in a circular order. So the only difference was where to find the answer for two different condition cases. One when we ignore the last house, and one when we ignore the first house.
Yeah.
So then we solve two ways. We can solve problems in two ways. One is we can start from the smallest problem and build up to the biggest. Another was, I think, what did we do? I don't remember the last method. The second.
Yeah. So basically we did what Drishan said. We looked at what types of problems can be solved using dynamic programming, and we said that basically broadly there are two types of problems that you would want to approach using dynamic programming: optimization problems as well as combinatorial problems. And we looked at the general framework for solving a DP question. So it's basically a divide and conquer paradigm which we use, wherein we solve smaller problems and then we combine the smaller problems to solve a bigger problem. And the only difference is here that we have sub problems or the smaller problems which need to be solved more than once. The same problem needs to be solved more than once. And that's why we said that we might as well store the value of that or the result for that smaller problem so that we can reuse it later on. And in that framework, so basically we just said that the basic framework is divide and conquer. And we said that we want to reuse the solution of an existing subproblem. That was the basic idea. And we said that there could be two ways you could go about reusing these the solutions of subproblems. One is you could build the solution in an incremental manner, starting from the smallest subproblem and gradually building up to the largest problem, which is the original problem. And the other way, which I have not yet discussed, is basically if we start from the biggest problem, and we gradually build our way or we solve that biggest problem, and in the process, whenever we encounter a smaller sub problem, we check if that sub problem has already been solved or not. If it has, then we reuse it. So that is something that we have not yet discussed. So this is the general approach that I told you how to go about solving dynamic programming questions. And we looked at a lot of one-dimensional sub problems. So we looked at sub problems which are one-dimensional, and mostly they involved 1D arrays. And at a very high level, they were the sub problems for a 1D array were prefix or suffix arrays. And we saw at least two types of decisions that we could use in solving these problems. We looked at the include exclude decision, and we looked at the decision wherein we find the solution to the sub problem including that element. So those were the two sub problems. Those were the two types of decisions that we looked at. And and we also and we saw that all these were basically order n DP. So we were able to solve the original problem in order n. So every sub problem was solvable in order one time. So this is all that we have done so far. Today we will build on this, and we will look at, to start with, we will look at 1D DP again. So we will look at one-dimensional sub problems, but the solution, the computation of each of these sub problems itself takes ordered n time. So that's basically what we will look at in the first half, time to compute a sub problem. So today we will look at that, and because of this reason that a sub problem takes order n time, the overall complexity of the solution becomes n square, because there are n such sub problems that you have to solve, and every such problem takes order n time to compute. So a total of n square time goes in solving the original problem. So that's basically the thing that we will look at. This is the first, this is the agenda for the first half of the array, first half of the session. So did you guys, I gave you a couple of questions. In fact, on Slack, I posted more than a couple of questions. Did you guys try the longest valid parenthesis question? Longest valid parenthesis substring. This question? Were you able to do it, or do we should we discuss it now? Yeah, we can discuss it. So in the fundamental structure, if you see in all these 1D DP problems, was that most of the problems that we discussed had told you to find some subarray, with a specific criteria, right? Like we looked at the wiggle subarray, or we looked at the maximum sum subarray. So all of these problems told you to find a subarray. And that's why we use that decision that we want to compute the solution for a sub problem, including this element. So that basically helps us to solve this sub problem in order one time, right? So this question, it's also the longest valid parenthesis substring question, is basically you have to find a substring. And so one of the thoughts that should come into your mind when you are told to find subarrays or substrings is DP, using this type of decision. There are other things also, like we discussed how we can go about solving subarrays using the view that I gave you, right? Using hash tables and maps. So that is also another standard way you can go about solving subarray problems. And then the third way is two pointers. So broadly, any kind of subarray problems can be solved using these three techniques. This was maps or hash tables. And we also looked at two pointers, these are index-based two pointers, which can be used to find a subarray with a certain property. So this is how to find subarrays with a specific property, correct? So in the longest valid parenthesis question, again, we will say that the longest valid parenthesis, so we will again go about the same approach. We will say that the longest valid parenthesis will end at some index, right? So it could end at this index, or it could end at this index, or it could end at this index. It could end at any of these indices. So what we will do is we will compute the longest valid parenthesis ending at a given index for all the indices. And then what we can do is we can take the maximum for all I, right? So that's the first thing that we said. We said that we want to compute for all I the longest valid parenthesis ending at I. And we can then take the maximum. Take max. That's the basic idea. Now, so for computing the longest valid parenthesis ending at I, what can we do? Now here you will have the decision. The decision is that if you can either go ahead with a subarray of size 1 or a subarray of size greater than 1, right? So there are broadly two cases here. If the ith element is an opening parenthesis, then you know that the longest valid parenthesis ending at I will be 0, right? Because you cannot have any valid parenthesis ending at I which ends with a opening brace, right? So for this it will be 0. That's the first case. And the second case is, what if this is what if the last element is a closing parenthesis? And that's basically when we have to decide what could be the longest valid parenthesis ending at I. So what do we do in this case? Any ideas? So we have to basically, if this is our closing parenthesis, we have to find the matching opening parenthesis for this, right? So where can this matching opening parenthesis be found? That's the first question. Where can it be found? Any ideas?
Well, we would maintain a stack.
Stack is fine. Like, how do you do it using DP? Like,
no, sir.
Okay.
Until we find a suitable match, we maintain a stack, and when we find a suitable match, then the remaining sub problem will be DP of that I minus 1. Suppose at J we find a match.
So how do you find a suitable match using stack?
So I would, if it's a we are looking for the case when it's a ith element is a closing bracket. So whenever I iterate from I minus 1 to 0, whenever it's a closing bracket, I push it, and whenever it's a opening bracket, I pop it. And when for an opening bracket, whenever the size becomes 0.
No, that is not right, because you could have something like this also, right? So you will report here only. Here it will become
I'm
0.
Saying I also I will say that whenever size of the stack is 0.
Okay, size of the stack is 0. So for every closing parenthesis, you will push it, and for every opening, you will pop it, right?
Yeah.
But here it will become 0, right? If you come from here. Okay, you are saying you will push this also from I, not from I minus 1.
No, I will push from I.
Yeah, that could be done, but that will take order up to order n time, right? For a particular index. Can you do something better? Can you use a sub problem here? So think about I minus 1. If you are at I, for I minus 1, you have already computed the longest valid parenthesis ending at I minus 1, right? So you know that let's say this distance is D. You know that this particular substring is a valid parenthesis, correct? Beyond this, it's not valid. This is the last point where it is valid. So wouldn't that index be this index? If it is, that will be the index, or that will be the parenthesis which will match this parenthesis, correct? So what we do is, if it is a closing parenthesis, we look at this index. What is this index? This index is I minus dp of I minus 1, right? So this is the index. And if this index contains a closing parenthesis, then for this, it will be 0, right? So two cases. If this contains a closing parenthesis, then you will have 0 as the answer. And if this I minus dp I minus 1 minus 1, if this contains an opening parenthesis, then you have found a match for this bracket. Now, is that all? So will your answer be 2 plus dp of I minus 1, which is basically this length plus 1 plus 1 plus 2. Will that be all? That will not be all, because you could have another valid parenthesis here, right? So it will basically be this length plus 2. Correct? Did you guys understand this? How many of you understood this?
So what did you told last part?
Yeah, I'll tell you. So see, if this is a closing parenthesis, you have to find a matching parenthesis, matching opening parenthesis. So that matching opening parenthesis, if it is there, it will be here, right? Which is basically whatever is the maximum for dp I minus 1, you go one step before that and you look at that string, that character. If that character is an opening parenthesis, then you found a match. If that character is a closing parenthesis, then it will be 0. Correct? So if this is an opening parenthesis, then you have found a match. But will this be the longest valid parenthesis ending at I? No, there can be more. Like just before this index, whatever is the longest valid parenthesis ending at this index, you have to include that also in the actual answer. So your total answer will be 2 plus dp I minus 1 plus I minus dp I minus 1 minus 2 dp of that. Right? Does that make sense, Swami and Akansha? So that is basically the solution. Akansha, does it make sense? Yeah. So let's quickly see the solution. I will code it. Let me open it up. So what is the problem? Valid parenthesis, is it? What is the problem number? This one, 32. So let's see. So now again, we will build on from the smallest to the biggest. So this is the size of the string. And I will have a vector, which will be my dp vector of size n. Let's initialize it with 0. I mean, it's okay. And what is the smallest subproblem? The smallest subproblem is 0, 0, right? So for 0, 0, it will always be 0, right? Even if it's a closing parenthesis or an opening parenthesis, it will always be 0, right? Next, I will start from 1 and I can go up to n. Now there are two things. So there is only one case when you will get something, which is basically when, so what I can do is, you can, let's write a simpler code first. I mean, you can get away with you can remove these codes also. So if it's an opening parenthesis, then dp of I will be 0. This actually you don't need because you've already initialized to 0, but still let's do it for the sake of understanding. And now if it is a closing parenthesis, then you are in the else part. You will look at I minus dp I minus 1. Correct? I minus 1 minus dp I minus 1. So you can check if I minus dp I minus 1 minus 1 if this is positive. If this is not positive, then you don't have an answer, right? So if this is going out of bound, then you don't have any answer. So you can keep it to 0. So we will not do anything.
So,
But if it is,
so can you explain this condition? I minus dp I minus 1 minus 1.
yeah. So let's see this condition again. So you have, you are at I. So let's call this I as 3 or 5. Okay. And let's say starting at 4, the length is let's say 2. Okay. So what does that mean? That means the whatever is the longest valid parenthesis is here. So you want to look at this character. So what is this index? This is I minus 1 and the total length is 2. So what will be the index 1 less than the last or the first index of this? It will be this index minus the length, right? If you subtract to an index from a length, you will get 1 less than the start, right? So you can do I minus 1 minus dp I minus 1, and that will be this index, right? You can take an example also. If this is index 2, right? So 4 minus 2 is 2 if the length is 2. 4 is I minus 1 here, and this is 2, right? Is that fine? So we want to look at this character. So we are just checking if this index exists in the array or not. If this index does not exist, then for this closing parenthesis, I don't have a match. So if this goes, if this becomes negative, if this index becomes negative, then you don't have a match for this. So then it will be 0. You have already initialized to 0, so don't need to really bother about it. Like you can leave it as it is. So I'm only taking when it is greater or equals 0. So that's basically the condition. See this, it will make more sense. So I minus 1 dp I minus 1 minus dp I minus 1. If that is positive, then I will check. So what is the check? The check is that if S of this is an opening parenthesis. If it's a closing parenthesis, again, it will be 0. So I don't need to bother. I have already initialized it to 0. So I don't need to bother. So I can say that dp of I will be at least 2 plus dp of I minus 1. Correct? And I just have one more thing, which is basically to increment this with the largest which is there before that. So I can check for that. So basically, if I minus dp I minus 1 minus 2, if this is positive, then I can just increment it by this as well. So that will be the answer. And you can take a minimum, which is 0, and you can keep taking the running maximum because it could end at any of these indices, and return this. For empty, just take care of that.
सर I minus dp I minus 1 minus 2 इंडेक्स मतलब वो हो गया तो
हाँ, तो यहाँ पर चेक किया ना हमने कि वो अगर पॉजिटिव है तो, अगर नहीं है तो मैं कुछ नहीं कर रहा, जो आंसर है उतना ही है, अदरवाइज आई एम इंक्रीमेंटिंग इट.
ठीक.
Right? Did everyone get this? So you can remove this line also. All these lines you can remove because you have already initialized it to 0. So don't bother about it. So just this will also be fine. What did I remove? And this should be, if I remove this, it should be fine, right? Why didn't this work for this case?
Sir, if DP of like if ARRI is also like a closing brace, then also it will execute the condition, I believe.
Right. So you don't need that. You only want it for. So yeah, you cannot remove that. Makes sense. You can either put a high level if here only. Can I? But I will have to check this if. हाँ वही ये डालना पड़ेगा. Then you can remove, which is the same basically. Okay, so this is how you do this question. It's a, once you know the trick, it is fairly simple. Like, okay.
Could you explain the dp of I minus dp of I minus 1 minus 2 part?
Yeah.
Why were we checking for that?
Yep. So essentially what we are doing is, once I have found a match for this opening parenthesis, I need to, so I want to find the maximum length of longest valid parenthesis ending at this index. So will that be only this much? No, right? It can be more than that. Yeah, okay. So it can be this also, whatever this length is. So you are doing this entire thing.
Okay, I got it.
Yeah. Cool. Any more questions you want to discuss from yesterday? Let's do one more question. This is also 1D DP. Try this 1359. So what is the decision here? So think about placing the last order. It's the same decision basically, that just assume that you have n-1 orders already placed in some arrangement and try and place the last order. What is the decision? It is very similar to the decisions that we have encountered so far. You are looking at the last order or the first order. think about where all can you place the last order. So the last order is a pair. Let's call it P and what is the nomenclature? P and D. So P and DN. Where can you place the last order? So you already have n-1 orders placed in some way. You don't care. It is basically you have, yes. So when you have already placed n-1 orders, you have 2n-1 such 2 into n-1 such dashes, right? So now let's think about where can we place the last order. So think about this. Where can you place the last order? P, wherever you place P, you will have to place D after that, right? So what are the places? Pn can be put here, or 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 here, right? So Pn can be put in any of these places. So let's say Pn is put here. When Pn is put here, where all can you put Dn? Dn can be put here, or it can be put here, or here, or here, and so on till here. Correct? So for, if you place the Pn here, which is to the leftmost of the first parcel, you have these many possibilities for Dn. How many these are? These are basically 2n-1 plus 1, right? You have one more space. Whatever is the total number of elements that you have already placed plus 1, right? So if you place Pn here, you have these many options for Dn. Is this clear? First.
Sir, could you repeat it? My network is.
Yeah. So think about where do you place the last order. So that last order, wherever you place Pn, the Dn will have to be placed after the Pn, right? That's the constraint in the question. So if you place a Pn here, where all can you place Dn? You can place it here, 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 so on till here. So now if there are, how many dashes were there? There were 2 into n-1 dashes, right? For n-1 orders you've already placed. So each order is a tuple. So 2 into n-1 orders dashes are there. So how many spaces are there? You have plus 1 space, right? So you can place your Dn in any of these slots once you have placed your Pn.
Sir, how it's 2 into n-1?
N-1 orders you have fulfilled. So every order is, you have fulfilled P1, D1, you have fulfilled P2,
Okay.
D2, and so on till Pn-1, Dn-1, right? So all these have an arrangement, and you are putting the last one. So this is the total number of ways you can put Dn if you place Pn here. Now what other possibilities of Pn exist? Pn can be placed here also, right? So if you place a Pn here, where all can you put Dn? You can put Dn here. If you place your Pn here, then you could put your Dn here, or here, or here, and so on, right? So how many places are there? You have basically 2 into n-1. No, -1, not -2, because you've just left out this space. You can place Dn here also, right, Karan? Yeah. Now, similarly, if you place your Pn here, you can put your Dn here, here. So how many places can you, where all can you put? What is the total number of places? It is 2n-1, -1. Correct? And finally, the last case is if you place your Pn here, what is the, where all can you place Dn? Just here, just one case. Correct? So the total number of places where you can place Pn Dn is summation 2 into summation, it is from 1 to 2n minus 1 plus 1. Correct? So what is this summation? This is n plus 1 by 2. So n is this. So this is basically 2n minus 1, right? So n plus 1 by 2. So 2n into 2n minus 1 by 2. So this will be n into 2n minus 1. So for every arrangement of these n minus 1 pairs, you have n into 2n minus 1 possibilities of putting the last pair. Is this clear to everyone? Correct? So what is the total number of ways you can put n items? This is basically this into the total number of ways you can put n minus 1 items. So this is the answer basically.
From where 2n minus 1
Why
minus 1
multiply?
came?
Where are you saying?
From where 2 into n minus 1 minus 1 came? थोड़ा नीचे.
ये वाला ना?
नहीं नहीं इधर नीचे.
ये?
नहीं इधर.
ये वाला.
हाँ हाँ.
This is, what was this? This is this part. This is basically, this is not the math. The math is from, you are summing from 1 to, what is this? When you simplify this, this is 2n minus 1, right? So you are summing 1 to 2n minus 1. So what is the sum? Sum is n into n plus 1 by 2, where n is the number of, n is the last number. So n, the last number is 2n minus 1. So n into n plus 1. So 2n minus 1 plus 1 by 2. So this 1 cancels, this 2 cancels. So you have n into 2n minus 1, which is what I wrote here. So you have n into 2n minus 1 possibilities of placing p and dn if you have for every valid arrangement of these n minus 1 items. Did you follow, Jadav?
Yeah.
So why
Yeah, so
is it multiplied into dp?
Because for for any such arrangement of these n minus 1 items, you have this much possibility. So think about this. So for the first, you have this many possibilities. For the second arrangement, you have this many possibilities. So if this was k, you would have k into this much, right?
No, sir. Actually, I'm not understanding the multiplication part.
Yeah. So think about this in this manner. If you have 4 ways of arranging a particular item, if you have 4 ways of arranging these, let's say till n minus 1. Okay. So you have 4 arrangements. Let's just arbitrarily draw any 4. Let's say this is not valid. So let's call this P1. Yeah, let's say this is one arrangement. You could also do P2 D2, P1 D1. So this is another arrangement. So for this arrangement, you have this many ways of, so for let's say you pick up this arrangement, you have n into 2n minus 1 ways of putting P3 D3, right? So from this, how many possibilities emerge? N into 2n minus 1 possibilities emerge for the total from P1 to P3.
Yes.
Right? Similarly, for this arrangement, again, if you pick, you will have again n into 2n minus 1 ways of putting P3 D3 in this.
Okay.
So you have another n into 2n minus 1.
Got
Right?
it, sir. Got it.
So you will sum this for 4
K.
times, for whatever is the k times. So this is a product then, k into this one.
Yes, sir.
Correct? Is this clear to everyone? Others? Shall we code it very quickly? This is a
4 times, like 4
no,
ways.
4 was just an illustrative example. Don't take 4. Any k. I was just trying to explain it.
Sir, I didn't understand how dp of n minus 1 equal to k.
Your voice is cutting.
Sir, I didn't understand how dp of n minus 1 is equal to k.
How dp of n minus 1 came? It did not come. So you are writing up, this is the recurrence, right? So this is the bigger problem in terms of the smaller problem. So now you have the smaller problem is n minus 1. So again for n minus 1 you will do the same thing, right? So we will build it from the first to the last. So we will build it for the smallest, which is just 1, n equals 1, and then we will keep building for n equals 2, n equals 3, and so on. Similar to what we have been doing all this time. Does that make sense? See the code. If you don't understand, then we can discuss.
So we're reusing the computed part again and again. That's why we're using dp of n minus 1.
Yeah, we are reusing whatever was computed till n minus 1, right? For n minus 1, just for that n minus 1. Correct? So that's why we are doing this. I will show you a state space optimization also through this question. But to begin with, let's just begin with this. So we want to go up to n. So let's just define it for n plus 1, because 1 to n we are going. That's why. So what is the smallest one? The smallest one is for n equals 1. So for n equals 1, you have p1 d1. So there is only one way of arranging p1 d1, which is you just put p1 and then d1. That's only the only arrangement. For others, what we will do is we will now go in a loop. So these actually need to be long because of the constraints. Let's define the modulo also.
So the space constraint would simply be carrying over the previous remainder value until n, right?
Yeah. So we could just use one single variable also.
Exactly.
Yes, sir. If we only require the previous state, we do not need to maintain a completer.
Yeah, I will first write it like this and then I will remove it.
Okay.
For some of us who don't understand that. That's why.
Why it's up to n plus 1?
This is 1 to n we want, right? So we want to store n in n. That's it. That's the only reason. So we want to go from 1 to n. So dp of 0 will be empty. dp of n will be for n. That's why. Index and this is the same, right? So we want to get a dp of n. So dp of n will be, the array will be of size n plus 1, right? For indexing into n. Otherwise, we could use dp n minus 1 also. That's also okay. Did that make sense? See this, then you will probably understand. So what is the, so dp of, let's first compute the value in a temporary variable. So what was the expression? 2 into, let me just see the expression. You have n into 2n minus 1, right? Yeah. So n into 2n minus 1, here you will have, so I into 2i minus 1, right? You were doing it for n. So this will be the temp, and then you can update your dp of I as you will have to do modulo all the way. So just do the modulos. This into temp. I mean, it won't get, just to be safe, right? And you will return dp of n. Yeah, I will tell you, Karan, why we are doing modulo. I'll tell you the fundamentals. I just finish it first. This will work down. So see the question. So see the question is telling return the result modulo 10 to the power 9 plus 7. I'll just take a moment to explain you what this modulo arithmetic actually means. Many of us keep getting confused for this. So what happens is, see, when you are adding or multiplying things, if you add two very large numbers or multiply two very large numbers, it can happen that the total product of this goes out of the range of an integer, right? So it can go beyond what an integer can store, right? You can store 2 to the power 32 minus 1, 2 to the power 31 minus 1 is the maximum that you can store for a 32-bit integer. So if this product goes beyond this, then there is a wraparound, right? It will start coming from the negative. So that's why it says that whenever you get a result beyond that, give it a modulo. So modulo basically means that return that modulo 10 to the power 9 plus 7. So this is well within the range of an integer. And what we obtain by doing a modulo is that we are able to reduce the result to a range, to a value that can be fit in a 32-bit integer. So that's why the question is telling you to take a modulo. Now, how the modulo arithmetic works is that if you have A into B, so the question is telling you to return A into B modulo something, C, right? So this basically is A modulo C into B modulo C modulo C. This is something that holds true. This is an identity. So we have to return A modulo B, A into B modulo C, right? But what we did was we did this so that A is also not overflowing, B is also not overflowing, and the overall product is also not overflowing. And the other thing we did was this into this can also overflow. So what we did was we took a long integer to store this into this so that it does not become negative. And then we took a modulo. Does that make sense, Karan? Like, did you understand what we mean by modulo? The total number of possibilities could become very large. I is an index, right? It is given, it is in the constraint. You are not doing anything with I as such. I is an index. So I can go up to 500 maximum. Yeah, and I did not take a modulo here also because I know that if I can be maximum 500, this can be maximum 500 into 999, right? So 500 into 999 is also within an integer. That's why I didn't take a modulo here. Otherwise, I should have taken a modulo here also at every step. The point about negatives was that if, so let's take a very dummy example wherein we say that the underlying integer can only, underlying computer can store only 4. It cannot store more than 4. Or so then what happens is basically if you tell it to store a number greater than 4, then what happens is it wraps around. So assume this is the spectrum of all the integers that can be stored. So this is the minimum that you can store. This is int min. And this is the maximum that you can store, which is int max. So if you get any value which is greater than int max, what it happens is, let's say this was 3 places here. So what it does is it wraps around and returns you this value, 3 places from here. So we don't want that. That's why what we do is whenever we get a product which exceeds int max, we immediately take a modulo. So once we take a modulo, we bring it here somewhere. Correct? And when we bring it here, we are good. So now there is one more thing that we could have optimized here, which is called the state space optimization, which I want you to show you. So in all these questions, whatever we have done, we did yesterday as well as today, we used only the immediate smallest sub problem to solve for the next sub problem, right? So for solving the ith sub problem or the sub problem of length I, we were using the sub problem of length I minus 1 only and nothing else. That together with the fact that we were computing the sub problems in an increasing manner from the smallest to the biggest, if we observe both of these points, then we can basically say that when we are computing for I, we only need I minus 1, right? So why don't I just keep a single variable which stores I minus 1, and using that I can compute I, and then for I plus 1 I can make that single variable point to this or give it this value, so that for I plus 1 I can reuse this, right? So basically we could have eliminated the use of an array completely. We don't even need an array in all these questions. We can just do away with a single variable. Does this point reach you? Do you understand this? So this is what is called a state space optimization. So we have optimized the state space. Basically, we have optimized the DP array. Instead of keeping a 1D array, we just need one variable.
Sir, could you repeat last part? Like I to I minus 1 wale.
So when we are computing for I, what are we doing? We are using only I minus 1, right? For computing I, we were only using I minus 1. We are not using I minus 2, I minus 3, I minus 4, any of those, right? So what I could do is, instead of keeping all these values in an array, I could just keep the I minus 1 and use it to compute I. And for the next iteration, I will be computing I plus 1 and I will be using I. So can I update that variable to take the value of I just before the next iteration starts, so that for the next iteration, I can use this again, right? So yes. For 0, for 1, we are using this. For 2, we are using only this. For 3, we are using only this. So why don't we just keep this, so that, and we keep updating it as we keep going. This is a idea that is used in a lot of places. So that's what we will do now. Instead of keeping this DP array, I could just keep a previous. And to start with, it will point to 1. It will be 1. Now, instead of this, I can just use this. And in the final step, I can make it point to the current. Correct? Clear to everyone? Everything that we did up to now, is it clear to everyone? Can I have acknowledgements, and then we can move on to the next set of problems? So this we will build up. When we use 2D DPs, again, I will show you how we can reduce our DP or dimension to only 1 instead of doing 2, because we might be reusing only the previous row. So we will see that when we are doing that.
Sir, as we are not using the array to store the previous, like which method we are using to to use the previous element? Like
what? Come again?
Like, as if you are not maintaining, as we are not maintaining array, so like what method we are using here to use the previous element?
We are just using the previous element. So we are just keeping a previous element which we keep on updating.
Yeah, okay.
Right? So why was DP1 is 1? DP1 is basically for n equals 1. So for only P1, D1. So what is the total number of ways you can arrange P1, D1? Only one sequence, P1, D1, that's it. You cannot do D1 P1, right? Because that's the constraint. So you have only one way of arranging P1 D1. So that's why DP of 1 was 1. Okay. So this is all about 1D subproblems using in order n. Today we want to look at 1D subproblems again, but we want to do them in, we will see that we will typically be requiring order n square time for that. So we will look at these kinds of problems today. So let's start with an illustrative example, and I will explain the essential concepts through this example. Let's start with this question. $139.
So will you be posting a list of all these DP questions?
I have
separately?
already done that in the Slack channel.
Oh, okay.
Order n I have already done. N square I will do today. Is Slack links are working now? I mean Zoom links? No, they're not. I just pasted the link also. Okay, I haven't updated then. I will update again. 139 is what we are doing now. So this is a popular question which is asked in many, like this is a very popular question. This keeps on coming up, like Google has asked it multiple times, Uber has asked it. So when I was sitting for campus placements, this question was there in their online test. It keeps coming up everywhere. Any ideas? This is also a very simple, there is just a simple technique. So what is the decision here? So you have a string, let's call it lead code. You have a couple of words in the dictionary. Lead is one word and code is another word. And we have to basically find if you can segment this entire string into words such that every word is in the dictionary. Yes. So the decision is look at the eventual answer and look at the first partition. Where are you drawing the first partition? That's the decision. So that first partition, what are the possibilities? You could draw it here, you could draw it here. Let me use a different color. You could draw it here, 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 or you could draw it here, right? So you could draw the first partition in all these places. Let's say you drew the partition at I. What does that mean? 0 to I, this particular string has to be in the dictionary if it is a valid partition. So what is the, if you draw the partition at I, what is the possibility that you can partition the entire word? The possibility is if you can partition this entire string and if this is a word in the dictionary. Correct? So if you draw the partition at I, A of 0 to I should be in the dictionary, and A of I plus 1 to n minus 1 should be, you should be able to partition it. Should be partitionable, let's call it, if that's the word. Right? Do you understand this decision? First partition, where in the eventual answer, the first partition will be drawn at some index, right? It could be drawn here, it could be drawn here, it could be drawn here, any of these. So if the first partition is drawn at I, what is the constraint? That the word that you have seen so far from 0 to I, that should be in the dictionary, because it's a partition that you have drawn. And after that partition, whatever string you are left with, you should be able to partition that. Correct? Do you understand this?
Sir, why should the second condition also be true?
Why should? Come again?
Why should the second condition also should be true?
How, like, so if this is a valid partition that you draw here, you should be able to partition this also, right? Into appropriate substrings. Like, if this is not true, then this is not a valid partition, right? So leet code, if you are, what is the partition? What is one possible partition which you could have? You could have a partition like this.
After T. Yes.
So essentially, let's say, so you should, this particular word should be in the dictionary and this particular string should be partitionable. Because this is the first partition, that's why we are saying that this particular word should be in the dictionary. This is the first partition. Right? And we will basically take it for all the i's. So for all the i's, we will find this. And if there is a true for any of the i's, then that is then the entire string is partitionable. Yeah, it is very similar to palindrome partition.
So you are saying if a part of word is partitionable and it is present in dictionary, another part should be partitionable.
For that partition to be valid, that particular partition.
So the another part should also be in dictionary, right?
No, should be partitionable, because that's what we are not dividing it into two partitions. We are saying that you have a particular string which is there. We are, look at the eventual answer. Let's take a more complex example. Let's take cats and dog. Let's say you have cats and dog, and you have all these three words in the dictionary. You have cats, you have and you have dog. So all these words are in the dictionary, let's say. So what is one valid partition of this? This and this, right? So what I'm saying is, look at the eventual answer and think about the first place where you drew the partition in the string. So if this is the string, that first place that I could draw the partition could be here, 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 here, right? So if I draw the partition at a place I, then what is the condition for this to be a valid, what is the condition for this particular string to be a valid partition, this particular string to be partitionable if I draw the partition at I? What is the condition? This is the first partition. So this word should be in the dictionary and this particular string should be partitionable. So this is a sub problem now that we get. It's a smaller problem that we get, which is a suffix problem. Right, Jadav? Think about, yeah. So we are basically making a decision on the first partition. That's what we are saying. We are saying that the first partition could be anywhere. It could be at index after index 0. Just a second. It could be after index 0, it could be after index 1, it could be after index 2, so on till it could be after index n or n minus 1. So if it is after index 0, what is the possibility that this is a valid partition? Your C should be a word in the dictionary, and the remaining, which is ATS and dog, that should be partitionable. Now this is another sub problem. So you will again use the same technique. Let's think about the first partition that I have to draw in this sub problem. So it could be here, it could be here, it could be here, it could be here, all the places, all these possibilities. So if I draw it here, let's say after ATS, which is here, let's say, so then you have ATS should be in the dictionary, and DOG should be partitionable. Correct? So this is basically the decision that we have made. Is the decision clear to everyone? Yeah.
Suppose C and cat both are there, and first we got C in the dictionary, and then we remove the C from the string. Then after that, AT is not in the dictionary. So will this not create any problem?
No, we are doing it for all possibilities, right? So when we partition, this branch might not return true. This branch might return false. But one of these branches, if it returns true, then you have a valid partition. Right, Vidyut?
Yes, yes, sir.
Every letter of the string should be in valid partition. What does that mean? Yeah, that's not valid. Lead K code is not valid if you have lead code.
So we could just check until the specific word is done, and if supposedly we are encountering cat first.
That's not correct, right? You have an example which will. So if you have, you can have CAT in the dictionary.
Yeah,
you can have CATS in the dictionary.
I was coming to that only.
Mm-hmm.
That all we need to do is check whether both the solutions exist. So we check with cat and also check with cats. We don't stop the loop.
Yeah, so that's what we are doing here, right? We are drawing the partition at CAT. Once we will draw a partition at cat also once, and then we'll draw a partition at cats also once. So when we draw at cats, we will get a solution. When we draw at cat, we will not get a solution.
Yes.
Right? Is this decision clear to everyone at least? So these are the decisions that you have to think on your own. So make sure you understand the decision, right? This comes from recursion only. Like we have talked about a lot of these kinds of decisions in recursion also. No doubts in the decision. So we said that what are the, let's use the framework that we designed. We said that we want to first understand whether it is a DP problem or not. So this is an optimization problem. So I will typically use dynamic programming. That's the first thing. The next thing, why is this is not really an optimization problem here, because you just have to find whether it is possible or not. I will show you an extended version wherein you have to find the minimum number of cuts that you can make in order to arrive at a solution. So this does not hold. Correct? Now, let's say we are trying DP. What we will do, we will come up with a decision. Correct? So here we are saying the decision could be that we are putting, where do we place the first partition? What are the possibilities? So that's the decision that we make. We could place so for every such, what will be the recurrence? The next thing is we will define the recurrence. So if we place the partition at I, our recurrence will be that A of 0 to I should be in the dictionary, and whatever subproblem you are left with from I plus 1 to n minus 1, this should return true. Then you can return true for this. So S denotes the solution of the existing, the complete problem, which is basically is the complete string partitionable or not. So it is partitionable if you have this kind of a condition for any I. There exists at least one I from 0 to n. Does this make sense, this recurrence?
Sir, what if the given S is lead code and the dictionary has lead and lead code? Are we going to return true or false?
We'll return true, right? So when we place the last partition, we will have lead code, right? In the lead code, we are trying all these partitions, right? So when we try this partition for empty, it is always true, you know, right? So this and this word will be in the dictionary. Yeah, so this is this recurrence clear to everyone? So from this recurrence, and hona chahiye, you're right. This will be an and. This should be in the dictionary and this should be true. So from this recurrence, you see that there is a subproblem, and that subproblem is a suffix array of the original problem, right? So that's the next thing you do. You have a understanding of the subproblem that it's a suffix problem. Now you try and draw the tree. I just told you that, right? So try and draw the tree for maybe 2 levels. If you have, what are the subproblems you will be left with? If you try the first index, you will be left with 1 to n minus 1. If you have 0 and 1, if you are drawing a partition after 1, you have 2 to n minus 1 as the subproblem. Otherwise, you have 3 to n minus 1 and so on till you have an empty subarray. This is an empty subarray, empty prefix array, suffix array, right? Now let's draw one more level. If you draw a partition at 1, what will you be left with? You will be left with 2n minus 1. Correct? If you draw a partition at 2, you will be left with 3n minus 1. So don't you see that you have the same subproblem that you are computing for different branches? Right? So this gives us the idea that apart from the recurrence, we also need to store the solutions to these subproblems. Correct? Is this part clear? The part where we are showing that the subproblems repeat? I want acknowledgements from many of you. Akash, is it clear? Akhilesh, Anirudh, Atharv, Divya, Ishan, Sonia, Tanishq. Tanishq has stopped speaking since a long time. Yeah. So now, so if this makes sense, then the 5th step is basically we are saying that. So at the 5th step, we say that now we have repeating subproblem. So let's take the approach of starting solving from the smallest subproblem to the biggest subproblem, right? So the smallest subproblem is your subproblems were suffix arrays, right? So what is the smallest subproblem? It could be an empty array, or you could have a subproblem of size 1 also. That's also okay. If you have a subproblem size 1, then you will have to check whether it is in the dictionary or not and return true if it is there and false otherwise. If you are using the smallest subproblem as an empty, then for that smallest subproblem, it will be true, right? Because that empty string is always there in the dictionary. Correct? So that will be the smallest problem, and then you will start building. So what is the next bigger problem? It is this. what is the next bigger problem? It is this. What is the next? This. So when you are at a given bigger problem, you use the same recurrence. So when you are at this problem, you are using the same recurrence. So now when you are here, this problem, basically, you will again do the decision that you can place a partition at any of these places, here or here or here. So let's try this. So if you're trying this, then this should be in the dictionary and this should be partitionable. So what does that mean? This should be partitionable has already been computed. So you can simply look it up from the DP table. Correct? So it's always from the smallest subproblem to the biggest subproblem, Karan. And get a feeling for it for 1 dimensions. 2 dimensions, it will become even more difficult to imagine. So we are building from the smallest to the biggest. And whenever we are at a subproblem, we are reusing the solutions of the smaller subproblem. We draw a partition here. We just check whether this word is in the dictionary and we check whether this is partitionable or not. And whether this is partitionable or not, that question can be answered in O1 time. Why? Because that you have already computed, because you are going from the smallest to the biggest subproblem. Correct? So for the ith subproblem, which is basically from I to n-1, you are using maximum OI time, right? Because you could place a partition here, 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 any of these places, and you are reusing. So the total time complexity will be summation OI over all I, right? So this will be order n square. Correct? Any questions on this so far? Does everything I have said so far make sense?
So could you repeat order of n square?
Yeah, think about it, Jadav. What are we doing? When we are computing the ith subproblem, how much time are we taking? We are taking order I time, right? Why? Because we could draw, we are trying all the partitions, all of them to be the first partition. This could be a first partition, this could be a first partition, this could be a first partition, right? So if this is a first partition, we are checking for this, whether this exists in the dictionary or not. That is, let's say we have the dictionary in a hash table. So that will be order 1, whether this exists in the dictionary or not. And whether this is partitionable or not, I can simply look up from the DP table. So this will also be order 1. So for a given partition, we are taking a constant amount of time, but we are doing this for all the partitions for a given subproblem. So we are taking order I time for a given subproblem of size I. So how much time and we are solving 0 first, then 1, then 2, then 3, then 4, and so on till n-1. So what is the total complexity? It is this much. And this is basically n into n-1 by 2, right? So this is order n square basically.
Okay, sir. Okay, got it.
Everyone gets an idea, is having an idea of how we are solving the smallest to, is everyone getting an intuition for this? The decision is fine. The decision, coming up with a decision is challenging, but once you know the decision, do you understand how we are going about doing this? If I give you the decision, will you be able to solve this on your own? That is the question. Decisions are tough. Decisions will come with practice. Like more you practice, more different types of decisions you will encounter. That's why my goal here is to give you the most common decisions that we encounter. Like, because that, like, I can only give you so much. After that, these decisions are very frequent decisions. Many questions you will get will have this decision. But that does not mean that you will not get questions wherein you will have a new foreign decision. You will have to think of that. That will come with practice. But once you have the decision, somebody has told you the decision, will you be able to do this? All the exercise that I have done so far. That's the question. If you will not be able to do that, then let me know. I can explain again. If yes, then we will look at the code.
Sir, you told that the two-part step O of 1 and O of 110. So how come it n square?
That is for a particular partition, right? at a given place if we are placing a partition, and we are trying all possibilities. We are trying a partition this, right? For a given I. So let's see the code. Things will become even more clearer. So we have a 1D DP, right? So let's build from the smallest to the largest. First, let's just, for the sake of simplicity, let's just store this dictionary in a hash table so that we can look up in efficient time. Because otherwise we will have to go over all the words in the dictionary. So let's do that first. Let's use a set. Let's call it diff. I will just insert it in the dictionary. So now I have the dictionary in a hash table. Now let's do the DP part. So we have a 1D DP wherein DP of I is storing whether A of I to n minus 1 is partitionable. And we are
so why are we adding in the set the dictionary?
Because when we are at a given I, we will look up 0 to I, right? In the we want to check whether that is in the dictionary or not. So that lookup will be
okay.
Constant time. Otherwise, it will take time. So let's build from the smallest to the largest. First things first, let's define the DP array. This will be a Boolean array. This will be of size n plus 1, where n is the size of the string. Because n, so at DP of n, we will store for the empty string. So let's initialize everything to false to begin with. The smallest subproblem is an empty suffix array. So DP of n will store the empty suffix array. I will just mark it true. Correct. And now I will start. From the next smallest to the next biggest. Now, when I'm at an I want to try all the partitions. So I will run a loop now.
So why is DP of n equal to true? Or why
n,
is the smallest subproblem?
It's an empty array. So DP of n minus 1 is only the last element. DP of n minus 2 is n minus 2 and n minus 1. That suffix array.
Okay,
so
so
DP
we're
of
going in reverse.
Yeah, we're going in reverse. You could go in the other direction also. It is nearly the same.
Sir, what is line 9 doing? Where
we are just storing it in a set. You will understand why we are doing it. Don't worry, we will see. You will see the importance of this here. Because when we are at a given I, we want to look up that word in the dictionary. So if we have a vector, we will have to go through the vector one by one and match. Right? So we just inserted it in the dictionary and we can look up in the dictionary in the hash table. This is a set, right? A hash table. Yeah. Any more questions?
Okay, got it.
So I actually encountered. I was thinking of if we go up from the 0th index.
Then also it's fine.
Wouldn't we encounter a problem there?
So you will have to shift your DP array by 1. So basically DP of I will store from 0 to I plus 0 to I minus 1.
DP of I will store 0 to I minus 1.
Yeah, that's how you will. Otherwise, how will you store the empty one? For the empty, if you want to store it in DP of 0, you will have to shift everything by 1, right? You cannot have DP of minus 1.
Okay.
So that's the reason. But if we are going from the back, we can use n.
Yeah.
So let's start this. So where will we start from? We will start from the first partition. So the first partition can be placed. So we have from, oh, I told you from 0 to I, right? The first partition, right? So I think this is fine. This is consistent with what I have explained on the board. So where we have to find from I to n minus 1, right? So let's try the partition at I. And we can go up to n minus 1. So we are trying all partitions here. Now, what string have I already found till now? I will just store that. Again, T. So when I will just append that to S of j. So basically, this I have to find whether this is in the dictionary or not. So if dict dot find of t is the end, so then I can continue. Basically, this is not a valid partition, right? Otherwise, I will have to check whether this is a valid word in the dictionary. So then I will have to check from j plus 1, right? From j plus 1 if that is partitionable. So if of j plus 1, not dp of j plus 1. So now both the conditions are true. I can mark this as true now. And I can return dp of 0. Ask me questions on this code. Yeah, it is for this. We want this to be a constant time operation. Otherwise, what we will have to do is we will have to look up one by one in the word dict array.
Sir, can you dry run, please? With example there.
Yeah, so line number 30 is basically, I am just making sure both the conditions are true. So in this line, I am ensuring that the prefix, the word that I have encountered so far is in the dictionary. If it is not, then I'm continuing, which is fine. Like I'm just moving on. If I come here, then I know that the prefix is in the dictionary. So the only condition that I am left with is I have to check if whatever comes after this partition, is it partitionable or not? So that sub problem I have to check. And that sub problem has already been computed because it's a smaller sub problem. So I am.
So could you dry in this particular example?
Yeah.
I had a question. Finding in the dictionary, won't it be order of the size of the string?
Finding in the dictionary won't be order. So it depends on the hash function that you are computing. If the hash function, so these are keys, right? So if the hash function you are computing is constant time, then it will be constant. Generally, it is not. It is for strings, the hash function takes time equal to the length of the string. So then the finding will not be, it will take the length of that string time. So this will be more than n square. You're right.
Yeah.
But it is obviously better than going through this array, right?
Yeah,
you don't have to. It is only order k, where k is the length of the maximum, the biggest length of a word in the dictionary. If you otherwise, if you have an array, you will have to go through that array one by one and check if word dict I equals t.
So we could straight away use a unordered map to reduce a 2 or 1.
It's the same. Set and maps are same. Why would that change with a map?
Because a map would use its hash key.
This will also use the hash key. The point is that the hash key computation might not be constant time. For a string, it is generally not. They work on all the characters of the string and come up with a hash value.
Oh, yeah.
So for the set also, it will take order k. For map also, it will take order k. That is not a factor here. So maps we use when we have to store a value also with for the corresponding key. Set we use if we want to store only the key. If we just want to check for the presence or absence of something in a data structure, we can just use a set. That should be enough. But if we want to retrieve the associated value also with that particular key, then we would need a map.
Okay.
Let's try run this.
So basically, sir, I had this doubt.
Yeah.
For every index, we are generating all the substrings ending with that index, and we are checking if that substring is present in the map or not, isn't it?
Yes, that's this part. That's this part. There is more to that. So whatever is left after that, that should also be partitionable. Because this is the first partition that we are drawing.
So J is the starting index of the string we are considering.
J is the, yeah, J is from I. So it's the starting index.
Okay. So once we find the string that is in the dictionary, we check if its next DP value is true or false. If it is true, then we will store true, else we will store false.
Yeah, you can break also. If you want to optimize it, you can break from here. Once you get a true, you can break this outer loop also. That will be some optimization that you can get. You don't have to further try partitions because you have to just find whether there is a partition or not. Let's try run this. I think things will become a little more clearer. But the whole point behind explaining all this was you should understand it at level 1. Otherwise, you will not be able to think yourself. If you are looking at things in like, if you are trying these things, unfolding the recursion in your head, when you are coming up with a solution, you will encounter all types of issues. So let's try run this. Let's say you have a dictionary. Let's take a more sophisticated example. Let's say we have cats and you have dog. So you have all these in the dictionary and you are given this string. Let's say you are given cats and dog. So what are you doing? For the entire so let's write it. So for every suffix, we are computing whether it is partitionable or not, right? So we start with the empty suffix, which is here. So this we mark it as true. Let's call it, I'm just writing it as 1. So this is partitionable. That's why I'm writing it as 1. Okay. And now I will start from here. So my I will be here at n-1. This will be my I. And now my J will start from I to n-1 to n-1. So J will only be here. And in my T, I will append G. So my T becomes G. So I'm basically trying to draw a partition here for this subproblem. This is the subproblem that I'm looking at. I'm trying to draw a partition here. So if I look up G in the dictionary, is it there in the dictionary? No, it is not there. So I immediately write a F here. Let's write this as T. So because T is not in the dictionary. Now I move my I to this n-2. So basically, what is the sub problem that we are looking at? We are now looking at this particular sub problem. So we will try this partition and this partition. So we start J from here itself. When we are here, we append O to T. So T becomes O because T is, we are resetting T to an empty string every time we start with an I. So T becomes O. We'll look up O. Is O in the dictionary? No. We move J to G. Now we append G. So we get OG. We look up OG in the dictionary. Is it there? No. So I will again, and after that there is nothing else. So I will write a false here. Now my I moves on to this. So now you have an I here, and you will now start your J again from here. So T is empty. When your J is at D, you will append D. So you are drawing a partition here first. Then you will draw here, and then you will draw here. So once you draw a you are looking at this sub problem. You draw a partition here. You see if D is there in the dictionary. No, it is not there. You move your J here to O. You append O here. You see if DO is in the dictionary. No, it is not. So you move your J here. You see, you append G. You see DOG is in the dictionary or not. Yes, DOG is in the dictionary. So if DOG is in the dictionary, you check if whatever remains, whatever sub problem remains, is that partitionable. So this is the sub problem that remains. You see, oh, this is partitionable. It's true here. So you will write it true here. And now you will move on. Your I will come here. You will again start from your J. You will try this partition, then this partition, then this partition, then this partition. So as you try, you will get D, then DD, then DDO, then DDOG. None of these are in the dictionary. So you will move on here, again J, NDDOG. Nothing, none of these are in the dictionary. None of these prefixes are in the dictionary. You will move here. So these are all F you are updating. Now you will move here. You will start with A, this partition. Is A in the dictionary? No. Is AN in the dictionary? No. When you draw a partition here, you get A and D as T. So you will check, is A and D in the dictionary? Now you get a yes. So what does that mean? That means that for this sub problem, you have a partition such that this particular word is in the dictionary. So you have to now check whether this is partitionable or not. So you will look up this value. So this is true. So you will say that this exists and this is partitionable. So you will make this true. And you will again continue F, F, F. Finally, you will get a T here because you will look up this value and you will check for this string to be in the dictionary.
Sir, if we were using a prefix array, what would be the adjustment to this algorithm?
Come again?
If we were using a prefix array instead of a suffix array, like starting from 0.
So you will have to check.
Like I was confused about how would we check the forward state, because we'd be required, if there's an index I, we'd be requiring the rest of the sentence to be valid as well, which would be able to check via a DP of I plus 1 instead. But that wouldn't have been initialized yet, or would have put it in its default value of false.
Come again? No, so basically if you are using a prefix array, then that is also fine. If you are at a given I, let's say you are solving this subproblem,
sure.
Correct? So you will look at the last partition. So that last partition could be here, or could be here, could be here. So if,
0 to I.
Yeah, so I to 0 to I if you are solving. So if you are solving 0 to I, your decision will be the last partition. So that last partition in 0 to I could be here, or could be here, could be here. So if this is here at this index J, then this particular string should be in the dictionary and this particular object should be partitionable. So this you have already computed because you are going from the smallest to the biggest, and you can find this. So when your J will again start from here and you will keep decreasing and appending.
Okay. So what?
So it's not the first partition, then it's the last partition. That's the decision.
Sure. Okay.
how can we solve it using a trie? We discussed this when we were discussing tries. If you attended that class, we had this lecture. So you could build a trie on this dictionary, and once you encounter a true, you can restart from the root. We can take it up after the class, Aman. I think we discussed this using a trie also in the class. I can send you the recording. We actually coded it also. Okay, so whatever I said, is this clear so far? Like 1D DP order n square, one example, representative example.
Sir, what happens when we do not check for dp of j plus 1 is true, but we found the word, the required word?
And that is also false, right? If we found the required word, we are checking for j plus 1. If j plus 1, dp of j plus 1 is false, then we don't have a valid partition there, right? That cannot be a valid partition.
But we found that word, right? Why are we returning false? We found that word.
We found that word, but that's only a prefix of the string, right? We found this word in the dictionary, but you are not able to have a valid partition for this, whatever, right? So if you cannot, even if you found a word, if you are not able to divide the remaining into partitions, then this entire thing is not partitionable, right? For this index, this is not a valid partition.
Yes, sir.
Is this clear?
Yes, sir.
So clear in the sense the running as well, how the algorithm is evolving, as well as how I went about solving it. Can I have acknowledgements if it is clear? We were just optimizing Utsav. So if we actually, for a given I, if we are already able to find a partition first such that this is in the dictionary and you have a valid partition for this, then for this you have a true in any case, right? So you don't really need to check for other partitions after this. For them also it may be true, it may be false, but that's the optimization that we do. So let's level up if this is clear, and let's try word break 2. $140. This will be tougher. This is actually quite hard. I mean, this is lead codes true hard. So read it. We will come to it because this will digress. Or okay, let's do it also. This is tough, but it will take. We'll do it. Any ideas? What is the problem here, or what is the difficulty here? You have to return all possible sentences. Let's say if you were to return the minimum number of partitions, then would you be able to do it? So let's say the question was the same. You had the same string and you had to partition it, but you have to use the minimum number of partitions such that each of those segments are in the dictionary, and you had to find that minimum number. Would you be able to do that?
So that basically will be the same code, right? The one we wrote previously.
Yeah, we will not break. The only thing is we will not break, and we will keep taking the minimum. So it will be, if that is in the dictionary, then so if we have to find the minimum. So the question is now that you are given a word, a sentence, and you have to find the minimum number of partitions you can draw in order to divide this word into segments such that each segment is in the dictionary. You have a dictionary. So the same decision, the first partition, where are you drawing the first line? So if you are drawing the first line here, then what is the answer? If you are drawing the first line here, then it is basically 1 plus whatever number of partitions you get from this subproblem, right? And then you can draw a partition, try and draw a partition here. So it will be 1 plus whatever you get from here. If these conditions are also met, if this is in the dictionary and if this is partitionable, then whatever is the minimum number you get from this plus 1. And you can take the minimum for all the partitions, all the possibilities.
Yes.
Do you understand this version of the question? That if you had to find the minimum, how would you do it? It's the same code. It's just that when you are breaking, you will not break in the code. And you will keep taking the minimum.
So what minimum we are taking?
So we will basically, so dp of I will basically return not true or false. It will basically return the minimum number of partitions with which you can partition I to n minus 1. I'm going from the back again, the same, everything is same. I'm not changing anything. So dp of I will represent the minimum number of partitions. The same problem, right? Subproblem is the same problem for a smaller data. So if I have to find the minimum number of partitions for this entire array, I am basically saying that that will be basically 1 plus the minimum number of partitions for this array, and you will take the minimum of that for all I.
Sir?
Yeah.
So for this problem, can we do it like this way? Like
Yeah,
first
one second. Let's first as you let's first get this clarified for everyone. Then we can discuss on that. Okay, just a second.
So why 1 plus?
For this, now you are drawing a partition here, right? So for when you're drawing this partition, you have 1 already, and whatever number of partitions you will get from here will be here.
Yeah, okay. Okay.
Does this make sense to everyone? If the question is that you have to find the minimum number of partitions?
Where are we storing this? I thought dp of I itself stores the minimum number of partitions.
So basically this is dp of 0.
Okay.
Now for each of them again, so the same approach, we will keep building from the smallest to the biggest. When we are at an I, we will do minimum of 1 plus dp of j for all j between I to n. And that one will only come if s of I to S of I to J is in the dictionary, and if this is not -1. Does that make sense, or should I elaborate this? If this does not make sense, then we will not do this question. This will become pretty tough for you. How many of you understand this? Can you add?
Sir, why we are not taking maximum?
We have to find the minimum number of partitions. So that's why we are taking the minimum.
Okay. Okay.
It's the same problem. I've just this problem is not there. So now let's think about another modification that we have done, that instead of returning the minimum, we have to return all possibilities. We have to find all the possibilities and return them. How do we do that? So one hint is it will require 2 passes. Gitansh, now we can hear out your solution.
So what I was saying, like we could pre-compute whether at a particular I by splitting we can partition it or not. Like we can partition into 2 halves or not. We can keep it in a DP table. And now for we start from the prefix. We start from the string or first letter of the string and construct the string. And for each I where I can partition the string, I will pass that into my recursion so that in the base case I can add that case to the answer.
Yeah, I got your idea, like what you're saying. That is actually how we will do it. So let's say we have this DP table already computed, the DP table that we computed in the previous question, wherein DP of I stores the maximum, stores whether this string I to n-1 is partitionable or not. Let's say we have already stored that in a DP table. That's the first pass, let's say. In the second pass, can you use this DP table to enumerate all possibilities?
Yes, sir. That would be simple.
There will be recursion.
Yeah.
How many of you understand this? How will we do that? We can use that to find all possibilities, right?
Yes, sir. Just a for loop and a recursion would do it.
Yeah. So what we will do once we have this DP array, we will basically iterate over this string. And obviously we will have our dictionary. And so we want to print the number of possibilities. We will have this DP array also. So we want to print the number of possibilities. So what will be the decision again for this recursion? The decision for this recursion will be, let's talk about the first partition. So if in this string, this is S, if this is the first partition that I draw, what am I left with? I am left with this. So I can just check if DP of I is true or not. If it is true, then I can add this as a word and start recursing. So I have to basically, so what will be the total, see the total, the entire recursion for this will be, look at the solution, look at all the possibilities that are there. Some of them will start with this, correct? There will be a set of sentences which will start with this. There will be another set of sentences which will start with this, let's say. There will be another set of sentences which will start with this. So the first level of thinking is that I will basically, so that's what I want to do. I want to enumerate all possibilities. First, I will enumerate all possibilities starting with this, then starting with this. then starting with this. So what is the sub problem? If I want to enumerate all possibilities starting with this, it is basically this array, right? All the possibilities for this, whatever you get, you can append this particular word and you will get this box. Similar to the subsets problem that we did. Correct? Does this make sense? Others? What if you understand this, what did we achieve by having the DP array? We optimized backtracking. How did we optimize backtracking here? When we want to enumerate all possibilities with this as the first word, we will not recurse into this if DP of this is false. Right? So we have optimized that backtracking. Do you understand this point? My question is, what is the significance of the DP array in this question? This could have been done like this only without the DP array, right? What did we achieve with this DP array? We have optimized the backtracking. Is this making sense that we have optimized the backtracking? In backtracking, what would you have done? You didn't even know whether this is partitionable or not, but you would have still recursed in this half also. But we are stopping that. Only if DP of this is true, I will go into this. Otherwise, I will not go. I will move on to the next. Right? Shall we code it if you understand all of this? I will take a pause and you can ask me questions if you don't understand. If you understand, you can act and we will code it.
You said 2 passes, right? Like what are 2 passes?
The first pass is basically we are computing the DP array. The DP array is the same as the previous question. So for a given I, we are computing whether I to n-1 is partitionable or not.
Yeah. Okay.
So this question is, Akansha, we are doing it in 2 passes. In the first pass, what we are doing is we are computing the DP array. And the DP array is the same as the previous question, that as what was for the previous question, that if DP of I will be true if I to n-1 is partitionable. Right? So this is the first phase. Exactly the same as the first question, the previous question. And then we will have the second pass. In the second pass, we will use this DP array to populate all the answers. So when we are populating all the answers, what we will do is we want to enumerate all possible ways you can break this, right? So let's say this is your string. What will you do? You can place the first partition here, here, here. So you will enumerate all partitions, all sentences with this as the first word. And then you will enumerate all sentences with this as the first word. You will enumerate all sentences with this as the first word. Correct? So how will you do that? You will find if this word is in the dictionary and if this DP is true. If it is, then what you will do is you will call the function for this and append this word, pass this word. So once you are here, you will get a valid string, which will be a sentence. So you can append that to the result.
So that if that DPI is true, that we are checking for that particular word in dictionary, right?
Yeah, see the code, you will understand. Let's do the code, I think. will make things more clear. Let's see the code first. So let's, first thing what I'll do is I will let me just copy the DP solution. We will not spend time on that. Let's just copy this code here. Oops. So now I have the DP array computed, and now I want to compute the result, right? So I will write a recursive function for doing that. Let's call it populate sentences. What will this take? This will take the string that I want to populate. It will take the dictionary. What else will it take? It will take the DP array. And we will keep a string which will be the current word. So this is basically all the parameters from the recursion. And then we will have some parameters wherein we will pass down our contribution. So that is this. And we will have the final set of parameters for the result. So this is the result. This is very similar to what we do in recursion, right? So what is the decision for this recursion? You are looking at the first partition. So we will come to the base cases. First, let's go to the recursive formulation. So what is the recursive formulation? Try all the partitions. One. So that's the decision. Let's try all the possible partitions as the first partition. This could be the first, this could be the first. For that, and we will also have a start.
So that partition is in DP array or the whole word?
It's in start to S, start to n-1.
Yeah, like is it in DP array or whole word that's given?
It is in the word, it is in the string starting from index start and ending at n-1.
Okay.
See the code. I think you will understand once you see the code. So you could try all partitions. Let's so, and similar to what we have been doing, we'll use a T. So we have this word now, this character in the string, and we will check if this string is in the dictionary. If it is not there, then we can simply continue. If it is there, then we will recurse. So how will we recurse? We will call populate sentences with S. Let's pass this start here just to be more legible. From I+1, we will now do the same dictionary, the same. If it is not, then we will do one more thing. We will check if DP of I+1 is true. then we will recurse. DP, and what will be the contribution at this step? It is this string. So this is this string T with a space. You could do it here only if you are getting confused, and you will have a result. So you will populate this basically. So you are basically populating for all the beginnings. Let's see the base case for this. So what are the things that are moving? Start is moving. That's it, right? Only the start is moving. There is nothing else that's moving. So the base case is if you reach the end. So if you reach the end, what you can do is you can push back the current contribution in the result. So we will basically be doing result dot push back the current contribution. But the problem is that there will be an extra space at the end of the string. So we will just take care of that. So we will get the substring of current beginning from 0 to the total length will be current of size -1. And we can push back this string. And return. And we can call this from here. Populate sentences. On start it will be 0 to begin dictionary, and DP will be there, and you will have current we will pass as empty string. Then there is no contribution here. We have the result, and then we can return the result. What is current? Yeah, you're right, Sonia. You could either do a space in between, then you will have to prefix, or you could do this. Karan, does this make sense? So this is basically from recursion. You are passing down your contribution, right? You can remove this parameter and populate your result here also, right? If you remember, we discussed this in recursion that what you could do is you could pass down the contribution at every step such that in the base case you will have a solution in the string, and which you can push to the result. So the contribution to begin with is empty. And what is the contribution of this step? It is the prefix. What is the prefix? T, it is this, T plus this. This is the contribution of this step. Right? So whatever I have already gotten, I am just appending the current partition to that. And I'm appending a space also. So the downside of that is that when I will get the string as cats space and space dog space. So I just remove the space here, the trailing space that remains. How many of you understood this? Can you acknowledge?
Sir, if you remove the DP array from populate sentences, so it will again be a simple recursive problem, right?
Yes, and it will be backtracking then. So you can, here we are prematurely ending, right? We are not calling it on I plus 1 if that is not a valid, if that is not partitionable. Correct? So we are, so that's why we are not, otherwise you would have called it for all and you would have backtracked that thing. So backtracking, we are saving time there. Yeah, Pradyum, is this fine? Ishan, is this fine? Karo ab try, but recursion is like level 1. I have told you many times. Like it is that only, like it's do the subset sum problem if you don't understand. This is exactly the same as subset problem when you have to find all subsets, or these are all like similar questions. This recursion. Okay, so people who did not understand, take some time to think about it, and I can answer your queries tomorrow or after the class. Let's move on, because the point of today's lecture is not explaining you recursion but DP. So let's move on to the next DP question. I just wanted to show you a question wherein we are using both DP as well as recursion. So it becomes pretty tough. Let's try a simpler question. Let's try 300. Pradyum, are you there? Are you following? Meet, are you following? Are you there? Nirav, are you following? Saurav, are you following? I think you are. Ujjwal, Utsav are following, I think. Yeah, so try this now, 300. Now another type of decision. भाई 11 बज गया. So let's just do this question and then I can give you some time to think on this. So I know this takes time, like understanding and getting a feeling of this takes time. So let's do this. So what you are given is, you are given numbers in an array. What you have to do is, you're given numbers in an array. What you have to do is, you have to find the longest increasing subsequence of this array. So a subsequence is basically you pick up some numbers from this array and you keep the ordering. So the order in which you pick up the elements remains the same as the order in which they were present in the array itself. And what you have to do is, you have to find the longest increasing subsequence. So for instance, if you see this question, this entire subsequence is a longest. Let's make this 8. Let's make this 10. So then if you see 2, 5, 2, 5, 7, 8, 10. This is an increasing subsequence. of length 5. Correct? 8, 10. This is also an increasing subsequence of length 2 of this array. So we have to find the longest increasing subsequence for this.
So basic intuition would be to find the longest subsequence ending at that particular I.
Yeah, it will be the same. So the decision is, the hint is that the decision is similar to what we've been doing for yesterday. Yesterday, we were looking at longest arrays, subarrays with a specific property, right? Today, we are looking at longest subsequences with specific properties. And the decision again is the first thought is that we will have like the longest subsequence will end at some index I, right? So it could end at this index, it could end at this index, it could end at this index. So the longest increasing subsequence will end at any of these indices, right? So we will try all the indices. So we will populate for a given I, we will populate the longest increasing subsequence for 0 to I. And this we will do for all the I's and we will take the maximum of this. That will be my answer. That's the first thing. Is number 1 clear to you? Similar to what we've been doing yesterday, like what we did yesterday. For subarrays we did, this will be for subsequences. Now, if this is clear, then what the task we are left with is, we have to find the longest increasing subsequence ending at I for 0 to I, right? So now we will compute this. And this is where we will use the decision. So in the subarray counterpart, what were you using? You had to find the longest subarray ending at I with some property, and you used a decision that you could either just have this element, or you could have a subarray of length 1, or you could have a subarray of length more than 1. And we basically looked at, so that was the decision that we were making. Here, what will be the decision?
So if you're looking at LIS ending at I, the brute force solution would be to simply traverse the previous elements and pick all of those which are lesser than the previous one.
Yes. So basically here the decision is that the longest increasing subsequence ending at I will come from, it will have one element which will be before I, right? And then you will have I, correct? So that element could be any of these, right? So that the element in the longest increasing subsequence ending at I, just before I, could be any of these, brute force, correct? So if it is this J, then how can this J be a preceding? If this number is less than this number, right, then we can say that LIS of I will be whatever you have gotten till J, whatever is the longest increasing subsequence till J, you can append this to that and you can get the longest increasing subsequence for I. Right? It's very similar to what we were doing for subarrays. The only thing was for subarrays, we were using I-1 only. We were not using anything else. Here we are using for all J's, we will basically find the longest increasing subsequence ending at J. And if that J is less than I, then we can append 1 to that to arrive at a subsequence ending at I. And we can take that maximum for all, we can take the maximum for all the j's. Does this make sense? Everyone understands this? Any questions on this? Very similar to the line of thinking that we had yesterday. The same type of decision, the same type of sub problem. So you can see that this is again you have repeating sub problems. When you are doing for I, you are reusing for j less than I, right? So when you will be doing for I plus 1, again you will be needing this, right? So you have overlapping sub problems here. The same sub problem is being needed again and again. So what you could do is you could use the strategy of building from the smallest sub problem to the biggest sub problem. So what is the smallest sub problem? It is a subsequence ending at 0. Only these are all prefix arrays, right? So what is the smallest prefix array? 0. I mean 1. And that will be the longest increasing subsequence ending at 0 will be 1. Correct? And then we can build up. So longest increasing subsequence ending at 0 will be 1. Then you can go for longest increasing subsequence ending at 1. So for that, you will again keep going from 1 backwards. And for every such j, you will see if this j is less than I, you can do 1 plus whatever you got from here. And you can keep taking a maximum also. And then go to 2, then go to 3. Finally, when you would have done it for n minus 1, you will have the answer. Because you want to find the longest, right, Karan? So all the subsequences that end at I, you have to find the longest.
Sir, wouldn't it give the maximum without using
So you are saying find the first j which is less than I, find the first j such that aj is less than ai and add 1 to that. That will be the answer.
Yes.
Is he correct?
Sir, I was thinking of a different approach. Like we can use the logic that we applied in the previous two questions.
Yeah,
like,
just 1 second, Saurav. Let's get Karan's doubt clarified.
Okay, sir.
Yeah. So Akansha has a counter for that. No, for this, why is it an issue? No, you can still have it, Karan, right? So let's say you have a 10 at I and you have a 5 here and you have an 8, you have a 7 and an 8 here. So now when you are doing for longest increasing subsequence ending at 5 will be 1 and ending at 8 will be 2, right? So the longest increasing subsequence ending at 10 will be these 3. Not 1 plus 1, 2. Because you don't know, so the intuition is you don't have an ordering between this and this, right? You don't know that this is less than this or this is greater than this. You just know that these two are less than 10, but you don't know how less that is, right? So you could have a greater number here such that you have a big chain here. And for this smaller number, you have a shorter chain. Did everyone did you understand Karan's doubt? It's a very valid question. Did you understand Karan's doubt and why it does not work like that? So Karan was asking that why do I have to do it for all j for a given I? Can't I just stop at the first j that I get, which is less than I, and increase 1 to that?
Sir, what are all j's? Like we are going for every number, right? Is it clear?
So basically we are saying that the decision is we want to see, the question is we want to find the longest increasing subsequence ending at I, right? So the decision is that the previous element in the longest increasing subsequence ending at I could be any of these, right? It could be this, it could be this, it could be this, it could be this, it could be this. So it could be any of these. So if it is this, then what will be the longest increasing subsequence ending at I? That will be 1 plus whatever was the longest increasing subsequence ending at this index, right? So that is what we are doing. The only thing is that this number has to be less than this for this to be a valid predecessor of the in the longest increasing subsequence.
Yes, sir.
Right? So that's the decision. Everything is oriented around decision. If you get an intuition for decision, nothing like it. That's basically what I'm trying to drive home, the point about decisions. That's the only thing. Here the decision is that the predecessor could come from any of them. So it could be this, it could be this, it could be this. Here the decision was that the subarray is of size 1 or more than 1. Another way to phrase it could be that the predecessor of this could be either n minus 1 or n. If it is n itself, then you have a subarray of size 1. If the predecessor is of size is less than n, then it could be n minus 1 only, because you have a subarray that you want to find. So that was what that's basically the goal. Giving you a feeling of all types of intuitions. See, if you dry run questions, codes, you will understand. I know. You break your head over some question, you will understand most of the questions. That's not the point. The point is how you arrive at it. Let's see the solution for this. Then I will pause for questions. I know it might be becoming a little too heavy. So we want to go from the smallest subproblem to the biggest subproblem. The smallest subproblem is the prefix array of size 1, right? So let's have a DP array for this of size n. Let's initialize it to 0. The smallest subproblem is 0, 0, 0. So the longest increasing subsequence for that is of length 1, just that element itself, right? Now I will solve for each of the i's from 1 to n. Now when I am at an I, what do I do? I will basically be checking for all the j's from I minus 1. So if this strictly increasing, right? If this is strictly less than nums of I, then you could possibly extend this, right? So then dp of I will be max of whatever you have seen so far, 1 plus dp of j. And after you exit, once you are here, you have a dpi. For I you have already computed. You will keep a running sum because the eventual answer could end in any of these fixes, right? And the subsequence could end in any of these. So we will just keep taking the maximum.
तो सारे इनिशियली 1 होंगे ना?
सारे initially 1 होंगे. Yeah, so the thing is that, yeah. So या तो फिर आप यहाँ से चालू कर दो, बट वहाँ से नहीं कर सकते चालू. Could handle these. So ask me questions if you don't understand this code. If you understand, you can ask and we will move on.
Sir, how to do the follow-up?
And log in.
Yes, sir.
Yeah. One second. Let me explain this and then we can discuss. Could you explain line 19? Yeah, sure. So this is basically the decision. What was the, this entire code is the decision. This entire code is the decision. When you want to find the longest increasing subsequence ending at I, what was the decision? Decision?
Compare all the previous substrings, sir. I mean, all the previous subsequences.
Yeah, the decision was on its predecessor. That its predecessor could be I or I minus 1 or I minus 2 or I minus 3 or I minus 4, right? So if it is, so that's what the J loop is for. So when we are at a given J, we are assuming J could be the predecessor. So if J is the predecessor, then what is the length of this subsequence? It is whatever.
The predecessor will increase by 1.
Yeah, so we have that 1 plus dp of J. And we are maximizing this across all J's. So we are keeping a running max.
Got it.
Sir, why can't J also start from the index as I?
You can start J from it's strictly increasing, right? So you will have to have an if here, if you want to do that. You can start from I, you can say that I is the predecessor, but for I, this will not hold, right? Nums of J less than nums of I.
Yes.
So you will have to have an if, special if here, yeah.
Why for smallest, why in line 16, you again dp of I equal to 1?
This was just to handle if the predecessor is I itself. So the predecessor could be I minus 1 and so on till 0, right?
Yeah.
So if the predecessor is I, what is the length? Just 1. That element itself, right?
Okay.
So that's what we initialized and then we started from I minus 1.
That one we wrote in, okay. That one we can, in line number 11, that, why that's required then?
So line number 11 is the smallest subproblem, which is a prefix array of size 1. So only 10. What is the longest increasing subsequence for only this? It is 1, right?
Can't the line 17 handle that?
We are running from 1. Yeah. Yeah, you can do that. Yeah.
को initialize कर दो 1 से.
Yeah, okay.
हाँ.
Line number 8 में 1 लिख दो सर.
अरे ये रहा, ऐसे बोल रहा है वो. इससे भी हो जाएगा. This is what you are saying, right? Right, Jadav?
हाँ, yes sir.
हाँ, तो ये भी चलेगा. यहाँ पर भी ईशानी सिंह के इसको यहाँ 1 कर देते हैं. That is also fine. And then we can remove this. Correct? Is this clear to everyone? Can you acknowledge if it is clear? I will take some names because I haven't done for a lot of time. Ashirwad, Is this clear? Divyanshu, Kusagra, I think it's clear for you. Sakshi, is it clear? Or did you get lost? Pradyum, is it clear? Are you even there? Yeah. अच्छा, बीच में चले गए थे क्या आप कहीं? हाँ, वो दिख रहा था, मतलब एक्नॉलेजमेंट्स नहीं आ रहे थे. मैं 2-3 बार बोला प्रद्युम का है, प्रद्युम का है. मेरे को लगा कि मोदी जी जो किट बांट रहे हैं आप वो लेने चले गए. अरे फट. ठीक है. So this is it. This is this question basically. Follow up order n log n. Meet, do you have any ideas? N log n?
No, sir, I don't have any idea.
Yeah, let's discuss it. Like I will also have to recall. So if I recollect in term now, like in the interest of time of everyone.
सर एक मेथड है n log n का.
तो मैप्स में स्टोर कर दो.
हाँ वो मैं देखा था वो n log n पे बस वो हम एक एरे ले लेंगे और उस एरे के अंदर पहले फर्स्ट एलिमेंट डाल देंगे. तो हाँ मतलब अगर अब जो 1 से चालू करेंगे लूप, अगर वो पहले वाला एलिमेंट फर्स्ट से छोटा है तो उसको रिप्लेस कर देंगे. और अगर अब जो नया एलिमेंट आ रहा है वो जो हमारा एरे है अगर वो उसके लास्ट वाले से बड़ा है तो उसको इंसर्ट कर देंगे, वरना उसके अपर बाउंड पे जाके रख देंगे. तो मतलब हमारे पास हमेशा लॉन्गेस्ट अब तक का लॉन्गेस्ट इंक्रीजिंग सब्सीक्वेंस उस एरे में रहेगा.
ठीक है, cool. Let's discuss it later. Okay. I mean it's a very special algorithm. So in any case during interviews I don't think that will be expected from you. But that does not mean we cannot discuss it. We can discuss it. Let's discuss it first thing in the tomorrow. I will recollect some basic nitty-gritty of that. Like I understand the high-level idea that Tushar said, but once I like understand the details, then maybe we can discuss. नहीं वो नहीं करना है. वो क्वेश्चन तो नहीं करना. वो क्वेश्चन मैं देखता हूँ, हाथ जोड़ लेता हूँ. नहीं करना वो है.
सर वो आपने वो मतलब बताया था ना वो ऑफ एन में वो पैरेंथेसिस वाला.
हाँ.
वो कब करवाओगे सर?
कौन सा पैरेंथेसिस वाला?
वो आपने बोला था कि वो एक पास में करना है. वो आपने परसों दिया था.
वाइल्ड कार्ड वाला.
अच्छा वाइल्ड कार्ड वाला. हाँ वो अच्छा क्वेश्चन है, वो करवा सकते हैं. ठीक है वो करते हैं. लेट्स फिनिश द क्लास. वो अच्छा क्वेश्चन है, वो करेंगे. 376 is the next question. This is simple, quite simple, I think.
सर इसमें और टर्बुलेंट में क्या डिफरेंस है?
निकालना है इसमें, उसमें सब एरे निकालना था. So this is also similar to LIS, right? You can keep, for a given I, you can keep two values. The length of longest turbulent subsequence ending at wiggle subsequence ending at I, such that this number is such that the difference is positive, and the other is such that the difference is negative, right? And then we can, for a given I, we can compute. Any ideas? This is very similar to, like, there is a common pattern, right? This is similar to LIS. So how did we go about doing questions yesterday? We looked at maximum subarray sum question, and from there, then we looked at a wiggle subarray question, right? Or product, maximum product subarray. This is also similar, like you just have to do it for the subsequence. Any ideas how to do this? Why is this such a tough problem? So think about you want to find the longest wiggle subsequence ending at I, right? You can do this for all the i's and then take the maximum. Yes, that's basically the answer, Drishan. You got it. So हाँ वही है, आइडिया LIS और टर्बुलेंस का मिक्स करना है, सही है. So for ending at I, you want to find the longest wiggle subsequence ending at I, right? So think about its predecessor again. Its predecessor could be either like this, or it could be like this, right? So if its predecessor is like this, then you can find the longest wiggle subsequence ending at J of this type and append one to it, right? So that predecessor could come from any of these. So you can, and if it is like this, then you have to find the longest of this type. Does that ring a bell? So you can keep two DP arrays, one for storing ending at I such that it is increasing from I minus 1 to I, from the previous element to I, and another ending at I such that it is decreasing from its predecessor to I. So for I, you have to compute both these values. So increasing at I will be, you can keep going for, you can keep, its predecessor could come from any of these, right? So you will go at a particular J and you assume this is the predecessor. So you will find the longest decreasing at J and you will append this. So it will be increasing. And the constraint is that this should be greater than this. Right? Do you get the idea? I have not explained it completely. You can give it a thought also, but like, how many of you understand this idea? Yeah, similar to what we have done. So I guess you will be able to do this. So let's not code this. I think you will be able to do this. Let's move on to a better question than this. Let's try this. This is a good question actually. $1027. How do you do this? This is also similar, but it's not exactly the same.
सर इसमें भी सेम ही करेंगे बट डीपी अरे में जो डिफरेंस है वो स्टोर कर देंगे जो दो एलिमेंट्स के बीच का डिफरेंस है उस सब सीक्वेंस के लिए वो स्टोर कर देंगे
वो स्टोर करने से हो जाएगा
फिर जब चेक करेंगे तो वो चेक कर लेंगे कि वो डीपी अरे मतलब जो डिफरेंस उनको चाहिए वो वाला है या नहीं
नहीं है तो आप छोड़ दोगे
नहीं है तो फिर उसके लिए 1 होगा लेंथ मतलब और कुछ कर नहीं सकते
नहीं that is not enough for a given j. So you are saying for a given j I will store the common difference of the maximum arithmetic sequence ending at j, just that.
Yes.
And I will check the common difference between I and j. If it is the same as that common difference, then I will add 1 to that. Otherwise, I cannot extend that chain.
Yes.
That is not correct, unfortunately. It needs more. You need more information than this. So think about, the point is that for a given I, for a given j, if you want to extend that chain j, that j could be a part of an arithmetic sequence with different common differences, right? Not necessarily, and any of those chains can be a valid chain that you can extend. So for a given j, you will have to store all the, like for a given j, for every common difference that it has encountered so far, you will have to store the maximum length, not just only for the maximum. Did you get what I said, Utsav? So here, the approach is exactly the same as what we've been doing so far. So you are at a given I, which you want to find the longest in arithmetic sequence ending at I. So you say that its predecessor could be any of these. So if you go at a given j, its predecessor could be j. So when will its predecessor be j? You will have to find the longest chain ending at j with the common difference ai minus aj. Right? And extend that by 1 to find the longest chain arithmetic sequence ending at I. Right? And you will have to do it for all the j's and take the max. Correct? Do you follow? Do you guys follow this? There is a difference. For a given j, I am not storing only the longest arithmetic sequence ending at j. For a given j, I am storing the longest arithmetic sequence ending at j, and I am storing for all common differences I am storing. So for common difference 2, I am storing, let's say the length was 6. For common difference 3, I am storing, let's say the length was 3, and so on. Now when I am at a given I and I have a j, I check ai minus aj and use that to look up for the common difference. What was the longest chain ending at j? And I increment that by 1 to find the longest chain ending at I. And I do that for all the j's and take the max. Does this make sense, Akansha? Did you understand this? Yeah, I will repeat. So the point is, when you are at an I, you want to extend the chain of a j. You are assuming j could be the predecessor of the longest chain ending at I. So if you are assuming j could be the predecessor, sir, you have to extend that chain of j, the longest chain of j, with common difference ai minus aj. Right? With that common difference, whatever was the longest chain, you have to extend that by 1. Right, Tushar? So for a given j, you have to store the lengths for all common differences. For common difference 2, you have to store the length. For common difference 4, you have to store the length. So give it a thought, I would say. Yes, we will use array of hash map. You're right.
What length you are talking about?
Which part?
Like
Dada?
for difference 2, we have to for length 5.
So difference 2 ending at j, the longest arithmetic sequence of difference 2 ending at j is length 5. The length of the longest arithmetic subsequence ending at j with common difference 2 is 5. That's the meaning of this line.
Like, so 5 is the indexes, can we say? Like?
No, 5 is the length. 2 is the common difference. 5 is the length of the longest arithmetic sequence ending at j. Ending at j with common difference 2. Common difference, you understand, right? It's an AP.
Yeah.
Right? Did you get an idea? Like at a very high level, you can work out the details. We will code it tomorrow. But how many of you understood the idea? Yeah, so try it on your own. It is not very difficult, and we will code it tomorrow. I will also share more questions on n square DP in the Slack channel today only after the class. So try them also, and we will discuss 1D order n square for some time tomorrow before moving to 2D DPs. Okay.
Sir, can I ask a doubt in try? I have a doubt in syntax of the try, not a question. It would take just 5 minutes.
Yeah. 1 second. So let me end the class and then we can. Okay. So, all right, guys. So I think we will continue tomorrow. I will share some questions on Slack and you can try them. But make sure all of this is clear before you come tomorrow. See, things will start escalating. Like today, even in the word break question, I saw many of you had many types of questions. So get some intuition, like you will have to work hard. There is no other substitute. There is no alternate here. But you can always reach out to me if you are having any kinds of questions in understanding anything. हाँ, क्वेश्चन मैं डाल दूंगा स्लैक पे और आपको टैग कर दूंगा फिर से, ठीक है? You had a doubt in the, so that's basically the class. Thank you for joining. And the class is officially now over. I am just taking questions of people. So if you have questions, you can stay around. Otherwise, you can go. Good night. Thank you.
In the word book too, while making understand, you said that minimum, we are storing minimum of first part and second part. So which part was that in the code?
Come again. In which question are you saying, Bijit?
While word break 2, while you were explaining, you to at first you came up with that we are storing something minimum of first part and second part.
Mm-hmm.
So in the, where are you using minimum?
No, we are not using. I just gave another question. That was another question. That if you had to find the minimum number of partitions, how would you do it? Like I just gave you an extension of the question, which is asked in interviews. Okay. Yeah, we can take questions one by one. The try question first, then current stout.
Yes, sir. Please write down the 3 lines of code that I am telling.
हाँ, एक second.
सर ट्राई में पहले हम वो एक नोड बनाते थे ना, ट्राई के लिए नोड, उसमें उसके लिए ऑब्जेक्ट डिफाइन किया था 2 क्लास के अंदर. तो उसका एक लाइन था ट्राई नोड स्टार रूट.
हाँ बोलो ना, हमको याद है, बहुत बार.
और ट्राई नोड डमी, और उसके बाद लिखा था रूट इक्वल टू एम्परसेंड डमी. ये लिखा था ट्राई कंस्ट्रक्टर जो था उसके अंदर रूट इक्वल्स टू एम्परसेंट डमी वाली लाइन जो है।
हाँ ठीक है।
तो डाउट ये है कि सर अगर मैं क्लास के बिना बाहर लिखूं इस लाइन को, इसी लाइन को कंस्ट्रक्टर में ना लिखूं इसको, तो ये एरर क्यों पॉप आउट कर रहा है?
क्लास के बाहर कहाँ लिखोगे
सर? जैसे कि हम ऐसे भी तो लिख सकते थे ना इस लाइन को, पहले डमी लाइन लिखा ट्राई नोट डमी, उसके बाद ट्राई नोट स्टार रूट इक्वल्स टू एम्परसेंट डमी, वो सही है।
अच्छा,
लेकिन ये एरर पॉप आउट कर रहा है।
नहीं वो सही नहीं है ना। क्या कंपाइलेशन एरर दे रहा है या रन टाइम एरर दे रहा है?
कंपाइलेशन टाइम एरर है।
हाँ तो वो कंपाइलेशन टाइम एरर है ना, क्योंकि वो उसके लिए आपको मेंबर मेथड्स और मेंबर वेरिएबल समझना पड़ेगा। क्लास है ना वो हमने क्लास बनाया था, तो क्लास बनाया है तो फॉर एवरी क्लास यू हैव मेंबर मेथड्स एंड मेंबर डेटा, ठीक है। सो मेंबर मेथड्स आर ऑल द फंक्शंस ऑफ द क्लास and member data is all the data of the class. So this class in itself is a prototype. This is not anything concrete or tangible, ठीक है। This is a data type. तो data type में आप ये नहीं लिख सकते कभी। Data type में you cannot initialize or do anything. This is just a prototype. You will create instances of this class, and when you create instances of this class, these member data will get value.
Okay.
Right? So that member data cannot have a value in the prototype itself. It's like saying कि मैंने आपके शरीर का एक स्केलेटन बनाया, तो मैंने आपके स्किन को भी कलर दे दिया।
लेकिन डिक्लेरेशन के टाइम पे इनिशियलाइज किया वो
डिक्लेयर
तो
नहीं है ये, वही तो, ये डिक्लेरेशन नहीं है। दिस इज नॉट अ डिक्लेरेशन।
अच्छा, इट्स लाइक अ इंट ऑफ इंट आई।
It's like, yeah, it's like this class is an int, it's like an int, correct. So ये declaration नहीं है, ये कोड रन नहीं हो रहा है, ये खाली एक डेटा। जब आप इसका ऑब्जेक्ट बनाओगे तब ये कोड रन होगा, और तब भी ये कोड रन नहीं होगा। जब आप इसका ऑब्जेक्ट बनाओगे तो वो कंस्ट्रक्टर कॉल होगा, और वो कंस्ट्रक्टर के थ्रू इसके डेटा को वैल्यू मिलेगा।
लेकिन सर अगर ट्राई नोट स्टार रूट इक्वल्स टू एम्परसेंट डमी, तो वो सही क्यों है फिर इस लॉजिक से? तो वो भी गलत होना चाहिए।
वो मैं कंस्ट्रक्टर में डाल रहा था, वो उस लॉजिक से नहीं चलेगा उसमें भी।
नहीं, वो कंस्ट्रक्टर में नहीं था वो लाइन। वो आपने दो लाइन सिर्फ ऐसे लिखा ट्राई नोट डमी, उसके बाद ट्राई नोट स्टार रूट इक्वल्स टू एम्परसेंट डमी, वहीं पे उसको इनिशियलाइज भी कर दिया, मतलब रूट पे पॉइंट करा दिया, रूट को डमी पे पॉइंट करा दिया।
ये लिखा था मैंने इक्वल्स एम्परसेंट डमी इन द क्लास का मेंबर डेटा में, ये क्लास के अंदर लिखा था मैंने।
हाँ, क्लास में लिखा था मेरे ख्याल से।
एक बार चेक करो आप।
I don't remember the particular question.
देख लेते हैं, एक सेकंड।
हाँ सर, ये मिल गया। ये क्वेश्चन था वर्ड सर्च 2 का।
वर्ड सर्च 2 का, एक सेकंड। ये मेरा ही है ना, किसी और ने ट्राई किया, पता चल जाएगा।
हाँ सर, लाइन नंबर, सर होल्ड ऑन, लाइन नंबर 62।
हाँ तो ये तो क्लास के अंदर थोड़ी है सर, ये तो फंक्शन के अंदर है ना।
क्लास सॉल्यूशन के अंदर ही तो है।
फंक्शन के अंदर है सर, ये फंक्शन है ना, मेंबर मेथड है। मेंबर मेथड के अंदर तो आप वेरिएबल्स डिक्लेयर इनिशियलाइज कुछ भी कर सकते हैं,
के अंदर कर सकते हैं, ठीक है।
इसके अंदर नहीं है ना।
ओके, अच्छा समझ गया। वो सिर्फ पब्लिक के अंदर नहीं हो सकता सिंपली, किसी फंक्शन के अंदर हो सकता है।
हाँ फंक्शन के अंदर तो होगा ही, वरना तो फंक्शन का पर्पस ही नहीं था।
हाँ ठीक है, ठीक है, ओके,
ठीक है,
हाँ
ओके। हाँ करण, 211 में देखते हैं। यार अब मेरा कौन सा है इसमें? 7 days अगो है क्या? ये वाला देखते हैं,
जो पहले है वो देखो।
सबसे फास्ट वाला।
नहीं, लास्ट वाला।
हाँ 5 days अगो वाला मेरा है। कहाँ पर लिखा है रूट इक्वल % डमी क्लास के बाहर?
यहाँ पे करके देख लेते हैं, मेरे ख्याल से ये रन कर गया था, मैंने ट्राई किया था। आप यहाँ पे वो कर
कंस्ट्रक्टर में लिखा है।
हाँ, लेकिन एक बार वो ट्राई करिए तो, मतलब पहले ट्राई नोट डमी फिर रूट को पॉइंट करा देते हैं।
यही बोल रहे हो ना आप?
हाँ हाँ।
सही है।
ये यहीं पे ट्राई किया था मैंने, तो रन किया था उस टाइम पे।
ठीक है, ओके। आई विल, मैं मतलब बताता हूँ आपको, एक प्रॉपर आंसर बताऊंगा, ठीक है? अभी मैं कुछ भी बताऊंगा तो वो वैलिडेटेड नहीं होगा।
ठीक है, ओके।
ठीक है, मैं आपको पक्का बताऊंगा बट।
ओके।
हाँ करण, आपका क्वेश्चन था अपार्ट फ्रॉम दिस। थर्ड लास्ट क्वेश्चन स्लैक में जो डाला है उसमें से, या आज जो क्लास में हमने किया उसका थर्ड लास्ट। वर्ड सर्च, अरे क्या है, वर्ड ब्रेक 2। हाँ वर्ड ब्रेक 2 में बताइए, मैं खोल देता हूँ।
सर लाइन नंबर 23 में वो कर प्लस टी प्लस एम्प्टी वाला क्यों हमें इनपुट करना पड़ रहा है?
करंट प्लस टी प्लस एम्प्टी, ये स्पेस क्यों इनपुट कर रहे हैं, ये डाउट है आपका? ये टोटल बेसिकली इसका आइडिया ये है कि अभी हम अपना कंट्रीब्यूशन पास करना चाह रहे हैं, तो अभी व्हेन आई एम हियर इनसाइड दिस, मेरे को एक टी में एक वैलिड वर्ड मिल गया है जो कि इस टाइप का एक वर्ड है इस सेंटेंस का, ठीक है? तो मैं क्या कर रहा हूँ, जो भी मैंने अभी तक ऑलरेडी कंस्ट्रक्ट कर लिया है स्ट्रिंग, उसमें मैं ये अपेंड कर रहा हूँ और फ्यूचर के लिए एक स्पेस भी दे रहा हूँ ताकि नेक्स्ट टाइम अगला वर्ड कोई अपेंड करे तो उसको प्रॉब्लम ना हो। Basically, when I'm here, I already have a word from the dictionary which you can append to the partition that you have already created so far. So partition that you have already created so far is in current. So the format of current is you have the word, then a space, then a word, then a space. So I'm directly appending the current word to that, and I'm then appending a space for future.
सर अगर ये एम्प्टी वाला नहीं देंगे तो क्या होगा?
एम्प्टी वाला नहीं देंगे तो ये स्पेस नहीं आएगा, कैट्स एंड डॉग पूरा साथ में आ जाएगा।
अच्छा समझ गया, ओके।
तो इसलिए हम लोग यहाँ पर आप देखो एम्प्टी आखिरी वाला स्पेस हटा दे रहे हैं। इसमें प्रॉब्लम यही हो जाएगा कि ये यहाँ पर जब आप आओगे ना, तब आपके करंट में cats space and space dog space आ जाएगा. तो इसलिए मैं यहाँ पर वो स्पेस नहीं ले रहा हूँ. आई एम टेकिंग द सबस्ट्रिंग स्टार्टिंग फ्रॉम 0 ऑफ लेंथ n-1. तो मैंने स्पेस हटा दिया है, और लीडिंग ट्रेलिंग स्पेस जो जिसको बोलते हैं वो मैंने हटा दिया है, और जो बचा है स्ट्रिंग उसको मैं पुश कर रहा हूँ रिजल्ट में. तो डॉग के बाद वाला जो एक स्पेस है वो मैंने हटा दिया है यहाँ पर.
ओके,
समझ आया? अदरवाइज आप यहाँ पर भी स्पेस दे सकते हो. करंट प्लस यहाँ पर स्पेस देना है तो भी दे सकते हो, ऐसा भी कर सकते हो. इसको बीच में भी स्पेस दे सकते हो. तो फिर आपको यहाँ पर ट्रेलिंग स्पेस हटाना पड़ेगा, लीडिंग स्पेस हटाना पड़ेगा. तो इसका यहाँ पर आंसर आप जब यहाँ पहुंचोगे तो आपका आएगा स्पेस कैट्स स्पेस एंड स्पेस डॉग. तो बेसिकली उस केस में आप ये 1 से पूरा का सबस्ट्रिंग ले लोगे तो ये चल जाएगा. ठीक है, समझ आया करण? या एनी मोर क्वेश्चंस? वाइल्ड कार्ड वाला क्वेश्चन करना है? अरे यार बहुत गंदा क्वेश्चन है वो. मतलब केसेस है उसमें बहुत सारे, और कुछ नहीं है. लॉजिक वाइज ज़्यादा कुछ नहीं है उस क्वेश्चन में. You just have to ensure you're not missing any cases. We will discuss those questions basically. We will have a class when we discuss those questions. ठीक है, तो उसमें कौन कौन सा है? डिकोड वेज भी अच्छा क्वेश्चन है वैसे. आपने डिकोड वेज 1 और 2 दोनों ही. डिकोड वेज में भी आपका वाइल्ड कार्ड तो मैंने इसमें दिया ही नहीं है वैसे. अच्छा, वाइल्ड कार्ड वाला मतलब स्ट्रिंग वाला क्वेश्चन. अच्छा हाँ, तो आर देयर पीपल, इनफ पीपल हु आर इंटरेस्टेड, or do you want to discuss it in the class? ठीक है, करते हैं. So इसमें दो चीजें हैं basically. See, you have some sequence of opening brackets, some stars, then you get closing brackets. So one approach that I used was you could greedily assign a star to an opening or a closing parenthesis depending on the need. ठीक है, so you could do that, keep doing that. So when you get a star, assign it either a opening parenthesis or a closing parenthesis. How will you do that? If your number of opening parentheses is more than the number of closing parentheses, assign it the closing parenthesis. If it is less, we will see. So now, so keep assigning that at any, and you keep counting the difference. At any point, if you get a negative difference, then what you need to do is you need to flip one of these stars to an opening parenthesis. So basically what I will do is we will keep track of, I will show you the code that is best. तुरंत हो जाएगा उससे. What is this question? Let me just find the question. I will just share the screen. Is this visible? Is this visible, guys? The screen? So what I am doing is, I have three variables here. One is the count diff, which is basically giving me the difference between the number of opening and the number of closing parentheses. I have count stars. So when I'm encountering a star, so count stars is basically keeping a count of all the unused stars. So basically at any point I will have some stars which I would have used, some stars which will be unused, and some opening and some closing parentheses. So count diff is keeping a track of the opening minus closing. Count stars is giving me all the unused stars which are possible, which are left, and count used stars are some stars which I have used. So these are the three things that I'm using. And what I'm doing is, see, if it's an opening parenthesis, then I'm not doing anything. My count diff will just be increased. If it's not an opening parenthesis and it's a star, then there are two things. What I will do is I will try to greedily use up a star. So for that, what I will do is that usage will basically depend on what state I am at. If I am positive in the differences, so that means that I have more opening parenthesis than closing parenthesis. तो मैं क्या करूंगा, मैं इस स्टार को यूज कर लूंगा टू क्लोज. ठीक है, तो मैंने यूज किया तो काउंटर यूज स्टार्स का बढ़ा दिया और काउंट डिफ माइनस माइनस कर दिया, तो मैंने एक क्लोज कर दिया एक ब्रैकेट को. ठीक है, और अगर काउंट डिफ नेगेटिव है तो मैं इसको ओपन करूं काउंट डिफ, और अगर काउंट डिफ नेगेटिव है, so that means you have more opening parentheses, you have more closing parentheses than opening parentheses. So what I will do is I will go ahead and open one of the previously closed stars. Which is what I am doing here. कि अगर मेरा काउंट डिफ नेगेटिव चला गया, सो स्टार में मेरा काउंट डिफ, सी when I have a star there will only be two possibilities. काउंट स्टार है टोटल नंबर ऑफ, सो स्टार्स दो टाइप के हैं. कुछ स्टार्स को मैं ग्रेडिली यूज कर लूंगा ओपन या क्लोज करने के लिए, और कुछ स्टार्स को मैं स्टार्स ही रहने दूंगा अभी. तो काउंट यूज स्टार्स मतलब ऐसे स्टार्स हैं जिसको मैंने यूज कर लिया है, और काउंट स्टार्स हैं वैसे स्टार्स जिनको मैंने अभी ग्रिडली जो अभी यूज नहीं हुए हैं. तो तो एल्गोरिदम यही है कि जब भी मैं एक ओपनिंग पैरेंथेसिस करना है तो मैं स्टार्स अपडेट नहीं करूंगा। अगर एक स्टार आया है तो मैं ग्रेडीली उसको ओपन करूंगा, मैं ग्रेडीली क्लोज करने की कोशिश करूंगा। तो ये क्लोजर है। और अगर वो काउंट डिफ 0 है, ये एल्स में आएगा वो, अगर काउंट डिफ 0 है तो। अगर वो काउंट डिफ 0 है तो मैं इसको खोल दूंगा बेसिकली, इस स्टार को ओपनिंग की तरह यूज करूंगा। अभी एक स्टार आया है ना मेरे पास इस एल्स इफ में, तो मैं उसको कैसे यूज करूंगा वो लॉजिक यहाँ पर है। ग्रीडीली मैं क्या कर रहा हूँ, अगर काउंट डिफ, अगर ओपनिंग ज्यादा है क्लोजिंग से तो मैं क्लोज कर दे रहा हूँ। तो क्लोज करूंगा, इस स्टार को क्लोज की तरह यूज कर रहा हूँ, तो क्लोज की तरह यूज करूंगा तो मैं यूज स्टार्स में बढ़ा दूंगा और मेरा अभी का काउंट डिफ कम हो जाएगा। ठीक है, ये एक केस है। द अदर केस इज आई कुड यूज इट एज अ ओपनिंग पैरेंथेसिस। So I will use it as an opening parenthesis when I will have equal counts of opening and closing parent. Then I will use it as an opening parenthesis. No, I have not used it as an opening parenthesis. I am keeping it unused. And this is the part when I get a closing parenthesis. So if I get a closing parenthesis, अगर मेरा काउंट डिफ पॉजिटिव है तो मैं कुछ नहीं कर रहा हूँ, मतलब खाली डिक्रीमेंट कर दे रहा हूँ। अगर काउंट डिफ नेगेटिव या 0 हो गया है तो मैं चेक कर रहा हूँ कि कैन आई ओपन वन ऑफ द प्रीवियस स्टार्स, कैन आई यूज वन ऑफ द अनयूज्ड स्टार्स बेसिकली। अगर है मेरे पास स्टार्स जिसको मैं यूज करके ओपन कर सकता हूँ तो मैं वो कर दूंगा। और अगर मेरे पास स्टार्स नहीं है तो मैं चेक करूंगा कि कैन आई ओपन वन ऑफ द प्रीवियस जिसको मैंने क्लोज करा था, वो काउंट यूज्ड में है, और वो है तो मैं इसको ओपन कर दूंगा। कुछ समझ आएगा? थोड़ा सा भी आया?
हाँ
सर वो वाला पार्ट समझ में नहीं आया जहाँ पे वो एल्स इफ काउंट यूज स्टार्स वाला।
ये वाला
सर लाइन 25 से
25 से यहाँ से ना।
हाँ,
तो बेसिकली मेरे पास अगर क्लोजिंग पैरेंथेसिस आ रहा है और मेरा डिफरेंस नेगेटिव हो गया तो मैं चेक कर रहा हूँ कि क्या मैं पीछे वाले किसी स्टार को यूज कर सकता हूँ क्या। तो दो केस है, अगर मेरे पास पीछे का कोई स्टार ऑलरेडी स्टार की तरह ही पड़ा हुआ है तो मैं उसको एज इट यूज कर लूंगा, तो वो ये केस है। काउंट स्टार्स मतलब काउंट अनयूज्ड स्टार्स है वो बेसिकली। तो काउंट अनयूज्ड स्टार्स अगर है मेरे पास तो मैं वही यूज कर लूंगा एज इट इज। और अगर मेरे पास एक भी स्टार्स नहीं है पीछे तो इसका मतलब ये होगा कि या तो मेरे पास एक भी स्टार ही नहीं है या तो फिर मेरे पास कुछ स्टार्स हैं जिसको मैंने यूज किया था। तो मैं चेक करूंगा कि, और यूज मैं सिर्फ एक ही तरीके से कर रहा हूँ, यूज मैं सिर्फ ओपन करने के लिए कर रहा हूँ और कोई तरीके से नहीं कर रहा हूँ। एनी स्टार दैट आई एम यूजिंग ओनली फॉर ओपनिंग, तो मैं ओनली फॉर क्लोजिंग सॉरी। सो मैं उसको रीओपन करने की कोशिश करूंगा। तो मैं चेक करूंगा कि क्या मेरे पास एक भी स्टार है पहले जिसको मैंने यूज किया था फॉर क्लोजिंग, जिसको मैं अभी खोल सकता हूँ। अगर है तो मैं उसको खोल दूंगा। तो खोलूंगा तो मेरा यूज काउंट कम हो जाएगा और यूज काउंट कम हो जाएगा और एक स्टार बढ़ जाएगा। ये स्टार क्यों बढ़ेगा ये आपको समझ आया?
हाँ ये तो समझ में आया।
तो बस यही है। और अगर ये दोनों ही पॉसिबिलिटी नहीं है तो मैं फॉल्स रिटर्न कर दूंगा, मतलब कोई पॉसिबिलिटी ही नहीं है बेसिकली इसको यहाँ पर वैलिड करने की। एंड वंस आई कम आउट ऑफ दिस लूप आई कैन ओनली हैव वन केस कि अगर ओपनिंग मेरे ज्यादा रह गई क्लोजिंग से तो मैं फॉल्स रिटर्न कर दूंगा, नहीं तो मैं ट्रू रिटर्न कर दूंगा।
सर तो मतलब एक बार जब एक स्टार ऑलरेडी यूज्ड अप हो चुका है तो उसको फिर यूज करने का मतलब क्या मतलब
यूज तो मैंने ग्रेडीली ओपन करने के लिए किया था ना, तो क्लोज करने के लिए किया था। तो व्हेनेवर आई गॉट अ स्टार, यूज मैं यहाँ पर कर रहा हूँ। व्हेनेवर आई एम गेटिंग अ स्टार, अगर मेरे पास नंबर ऑफ ओपन ब्रैकेट ज्यादा है क्लोज ब्रैकेट से तो मैं इसको यूज कर दे रहा हूँ क्लोज करने के लिए।
हाँ वो तो ठीक है, वो तो समझ में आ गया।
तो मैं
मतलब
उसको वापस रीओपन कर रहा हूँ।
अच्छा,
यहाँ पर
अच्छा ठीक है समझ गया।
और
है
किसी को समझ आया ये? मतलब मैं बोर्ड पे समझा सकता हूँ उससे
आ गया सर।
I will share this code on Slack. You can stare at it. And tomorrow, if you still don't understand, I can explain on the whiteboard. मीत, आपको समझ आया ये?
सर वो लास्ट में वो काउंट स्टार्स प्लस प्लस वाला समझ नहीं आया।
ये वाला ना?
सर नहीं, वो नीचे नीचे में।
ये वाला ना?
हाँ सर।
हाँ, ये वाला थोड़ा ट्रिकी है। इसमें बेसिकली मैं ये कर रहा हूँ कि अभी मेरे पास क्लोजिंग पैरेंथेसिस आया, ठीक है? तो मैंने क्या किया कि मैं इसके लिए एक पिछला वाला को ओपन कर रहा हूँ।
मतलब सर आप अगर क्लोजिंग आया तो जो आपने स्टार क्लोजिंग की तरह यूज किया था उसको हटा के इसको बैलेंस कर रहे हो, मतलब इसको
हाँ।
एज अ बैलेंस यूज कर रहे हो।
हाँ।
और उसको नॉर्मल स्टार बना दे रहे हो दोबारा।
किसको स्टार बना दे रहा हूँ?
मतलब जैसे कि आपने किसी स्टार को यूज किया था बैलेंस करने के लिए, है ना? तो अब जैसे तो अब आपके पास कोई क्लोजिंग ब्रैकेट आया तो इस कंडीशन में आप उस स्टार की जगह इस क्लोजिंग ब्रैकेट को बैलेंस करने के लिए यूज कर रहे हो और उस स्टार को दोबारा नॉर्मल कर दे रहे हो।
हाँ, समझ आया मीत आपको? वो स्टार मैं यूज कर रहा था किसी एक ओपनिंग ब्रैकेट को बैलेंस करने के लिए, तो मैंने उस स्टार को एज इट इज छोड़ दिया और मैं इस क्लोजिंग ब्रैकेट को पिछले उस ओपनिंग ब्रैकेट से मैंने मैच कर दिया जो इस स्टार को जो ये स्टार यूज कर रहा था क्लोज करने के लिए। सी बेसिकली आपके पास कोई एक एक्स्ट्रा सरप्लस ओपनिंग ब्रैकेट था जिसके लिए आपने क्या किया, आपने इस स्टार को टेम्पररीली क्लोजिंग की तरह यूज कर लिया। अब इन फ्यूचर यू गॉट अ क्लोजिंग ब्रैकेट, तो आप और आपका नेगेटिव हो गया डिफरेंस। तो आप क्या कर रहे हो, यू आर ट्राइंग टू फाइंड कि ऐसा कोई स्टार एग्जिस्ट करता है क्या जिसको आप ओपन कर सकते हो। तो अगर मेरे को एक ऐसा स्टार मिल रहा है तो मैं क्या कर रहा हूं, इसको मैं वापस स्टार बना दे रहा हूं और इन दोनों को बैलेंस आउट कर दे रहा हूं। राइट?
अच्छा ठीक है सर, समझ आ गया।
हाँ, हाई लेवल समझ आया। आप एक बार और मतलब ड्राई रन करना, समझ आ जाएगा। मैं शेयर कर दूंगा कोड फ्लैट पे।
सर वो लाइन 24 पे मतलब काउंट यू स्टार प्लस प्लस क्यों नहीं कर रहे?
यू स्टार्स प्लस प्लस नहीं कर रहे हैं, ये स्टार थोड़ी है। अभी अपने पास जो आया है वो एक क्लोजिंग पैरेंथेसिस है ना, इस वाले एल्स में आपके पास एक क्लोजिंग पैरेंथेसिस है।
हाँ।
तो आपके पास अगर ऑलरेडी एक स्टार अवेलेबल है जिसको आपने यूज नहीं किया है,
हाँ।
तो आप उसको एक ओपनिंग पैरेंथेसिस की तरह यूज कर दे रहे हो।
हाँ, तो मतलब हम स्टार को यूज कर रहे हैं ना अभी।
हाँ, बट ये डेफिनेट हो गया। बेसिकली यू स्टार्स में सिर्फ वो स्टार्स हैं जिसको आप चेंज कर सकते हो। इस स्टार को अब आप चेंज नहीं कर सकते।
ओके, तो हम यूज स्टार में उसको रख रहे हैं जिसको हम
हाँ।
सिर्फ क्लोजिंग ब्रैकेट रख रहे हैं।
हाँ, यू स्टार में सिर्फ वही रख रहे हैं जो सरप्लस ग्रीडीली हम क्लोज कर रहे हैं।
ओके।
सम ऑफ देम, दो स्टार्स का डेफिनेट क्लोजर आ जाएगा, डेफिनेट, तो उसको यू स्टार्स में नहीं रख रहे क्योंकि उसको आप दोबारा ओपन नहीं कर सकते ना, तो आपका ये लॉजिक गलत हो जाएगा फिर।
ओके सर।
हाँ, ये भी था, मतलब मेरे को अभी याद आ रहा है जैसे जैसे मैं बता रहा हूँ। ठीक है, तो आई विल शेयर द कोड ऑन स्लैक, you can stare at it, dry run it, but this was only my logic. Like if you have better logic, I think this can be done in a more neater way. तो अगर आएगा आपको आइडिया तो बताना। मतलब ये मेरा फर्स्ट थॉट नहीं था, मैंने आधा दिन लगाया था, बट हाँ ये यही आया था मेरे दिमाग में, तो मैंने ऐसे ही कर दिया था। ठीक है, ऑल राइट गाइज, चलो फिर, थैंक यू, गुड नाइट, टेक केयर, आई विल सी यू गाइज टुमारो। guys and girls. Good night. हाँ डीपी क्वेश्चन भेज दूंगा मैं.